Well, thanks very much, and I'm happy to be here and invited back again. I never know for sure whether I'll get that invitation back each year, but glad to do it. And so we are recording this today, and the goal is to try to make this into a podcast that'll be available for people to look at online afterward to extend the reach a little bit further. So you may hear from time to time some language for the viewers at home, so to speak. So it's my pleasure, as I said, to be here and to talk to you about optics and refraction. And because we are recording this today for teaching purposes, the recording will be distributed freely at no charge, but I don't want people reselling it to other people for money. There are images in there. I did my best to track them down. There's some that I'd really like to keep, and so I've attributed them to their sources whenever possible. So what are we doing here today? Why are we here? I know that many of you have an examination coming up, but I think that there's more to it than that. If you have a good understanding of the principles behind what you're doing when you take care of a patient, when you do a refraction, it can make a difference for your patients and for your own practice. You can do great surgery and have an excellent post-op result, but if you do a lousy refraction, the patient's going to think you're a crappy surgeon. So these little steps that it takes to understand the basics of optics to do a better job refracting is really the core of what we're here for today. I do want to thank, in particular, Dave Guyton, my mentor. Many of the slides here were borrowed from him when he first asked me to go and cover for him, giving a lecture one day, and he's been a great mentor and friend over the years. So I've broken the presentation up into 4 parts. The first part will cover the basics of optics, physical optics, Vergence, and lenses. Then, once we have the basics down, we'll get into specifically focus on refraction, from visual acuity testing to accommodation through refractive surgery and intraocular lenses. Then later in the day, we'll look at other optics of note, magnification, low vision, mirrors, prisms. And then finally, we'll wrap up with practical matters to take the principles and all the things we've learned in the first 3 parts and put them together into how to prescribe glasses, how the instruments work, and how to handle optics in the office, that is, patients who present with specific complaints related to their refraction. This is what people think about when they think about optics. They imagine a whole wall of formulas that are just this mass of math and science. And by the way, it is true that I have some training in engineering in my background, and I do some research in the area of optics. But for today, the purposes of today, I'll forget all that and try to break down these formulas into pieces that are actually end up being helpful to you and not your enemy. These formulas, the basic formulas, the power calculations, which are all a similar equation put together, the magnification formulas also related to each other. As we break them down bit by bit, they'll all begin to make sense, and then that wall of formulas becomes just a review guide, just like any other review page that you might have. And then I did want to also comment, there will be times when I'm telling you things that you may be surprised I'm telling you because they seem so obvious, but I find that if you put yourself in the situation that some of you may be in, where you're asked to, you're sitting across from somebody who has a question and you know the answer to it, but they're looking at the answer, but they're asking you the question. So even a simple question like, please state your full name, you might say, my name is, and then, just the anxiety of being asked a question. You can't even remember your own middle name. So in order to be able to get through that, you need to have some of these basic facts down in a very clear way. And then I do want to mention that I have a review manual that I've published together with Connie West, and just as a disclosure, we get a 15% royalty on each book, so we split 10 or 15%, I can't remember, so we split something like $4.70 or $7 or something like that per copy sold. But we'll get to that. You know, it's been really had rave. The second edition's coming out in April. The first edition had rave reviews. Someone named Kirk Carver says, as a reference tool, this little handbook falls short. As a learning tool, it is also lacking with little detail or helpful diagrams. So, you know, I just think it's a, you know, I don't think you can get any better than that in terms of enthusiastic reviews for this book. So, all of you optics studs out there, the purpose of the book is to give you practice, to give a chance to ask yourself some of these questions and to work it out. So that's the prelude. So now let's move into some of the basics and to the physical optics that underlie the principles that we're looking at. So in physical optics, we want to talk about the properties of light. I want to talk about polarization and diffraction and interference and scattering, all things that happen to photons, refractive index, critical angle, and total internal reflection. These are the basic things we're going to be looking at today. So the first question is, we're dealing with light. Is light, a simple question, is light a wave or a particle? And we can't even really answer that question clearly because there's no one theory that explains all of the properties of light. The wave theory says that light propagates as a wave with a certain frequency and wavelength. The particle theory says that light is a photon, a discrete packet of energy, where the higher frequency is the higher energy. And you can actually consider light as one or the other, depending on the situation. So in addition, we can think of light as a ray, and that's what we'll end up doing for most of the day. But that's not a physical concept, that's an artificial construct that we use for geometric optics. Light, when we think of it as a wave, is a tiny little bit of the electromagnetic spectrum, running from the long wavelength, the radio waves, through infrared, ultraviolet, gamma rays. All of this, there's all this information out there, electromagnetic information. Light is just this tiny little sliver, and we happen to have photoreceptors that allow us to perceive that information. If we had more sorts of receptors in our body, we might be able to detect ultraviolet or X-ray or even infrared. You could look at someone and get more of an infrared scan, see where they're warm or where they're not warm, or well, maybe there's reasons we don't have those abilities, but what we're looking at is a little sliver of our universe, but it's an important sliver. So when we think of light as a wave is going to have a certain frequency, that is, it'll cross the line a certain number of times, a certain wavelength, the difference between peaks. It's going to have a direction of propagation, and it's going to have an electrical field of orientation. So you'll have a vertical orientation of light, for example, or another wave of light may have an oblique orientation. The electrical field has particular orientations of any one light wave. And when we look at light coming in from the sun, then light from the sun is a whole bunch of light waves, each one with a different orientation in a different direction. That's unpolarized light. So polarized light is a subset of those light waves where all of the rays of light, all of the waves of light are oriented in the same direction. We can create polarized light by taking any unpolarized light source and passing it through a horizontal polarizer. Now only horizontally polarized light is passing through. Now this horizontally polarized light, it looks like ordinary light. You can't tell with your eye that it's any different, but you can manipulate it with filters and do different things with it. So in this example, we're just passing it through another horizontal polarizer, so all the light passes through. But what happens if we rotate that polarizer? If we rotate it, well, now none of the horizontal light gets through, and so on the other end, there's no light coming through. So polarized light can be manipulated with filters. And furthermore, there are birefringent materials that change the state of polarization of light. That's what happens in polarized microscopy. So we have the same situation here where we have two cross polarizers. The light's not getting through. We have an observer on the other end of the microscope. If we put a birefringent crystal material in there, like so, then some of that light will change its polarization. So a little bit will leak through with vertically polarized component, and it'll appear to light up in the black background so that you get these polarized light images where the birefringent material has changed the orientation of polarized light so some of it gets through the filter. That's polarized microscopy. And we've been working on that in a device that I'm developing that looks at polarization of light and the light that comes back from the retina. Unfortunately, no time to discuss that today. So that's polarization. Now what about coherence? Coherent light is when the waves of light go up and down in the same, are all going up and down in the same phase. All the peaks are lining up. So we can get coherent light out of a laser, but the way we used to get coherent light before lasers were you could take light and pass it through a little slit, and now all the peaks and valleys are the same. Now you pass it through a second slit, and so now the peaks and valleys of light emerging from these two slits are coherent. They're in phase with each other. Then when the two coherent waves interact with each other on a screen, you get interference. And you can get constructive interference and destructive interference. So constructive interference is when the peak from this one lines up with the peak from this one, you get a maximum. But when the peak from this one lines up with the valley of this one, then they cancel each other out and you get a minimum of light. So one is constructive interference, brighter light, or destructive interference where there's no light. And this interference has many applications in ophthalmology. One where it used to be used, but less often, is this interference in testing potential visual acuity. That is, if you have an eye that has a cataract, the cataract isn't going to do a good job of forming an image, but you can still get light into the eye. And if you can get two beams of light into that eye that are coherent, they then interact with each other on the retina. And so when they interact with each other on the retina, then you can get an interference pattern that's not formed until you're past the lens. And at that point, the image is formed, and you can ask the patient if they see the stripes or not. Interference is also used in anti-reflection coatings so that we can have light coming into some glass. Well, some fraction of that light is going to be reflected back towards the source, and that's going to cause glare. But if you coat that glass with a layer that's 1/4 wavelength thick, then when you have the light coming in, you'll still get the reflection back from the surface, but you also have this 1/4 wavelength thick coating, and that's going to reflect back as well. But now you see the valley of this reflection matches with the peak of this reflection, and so the two end up canceling each other out and eliminating the reflections. Now each coating is there for each different wavelength, and it works better for some than others. That's how you can recognize an anti-reflection coating. If you take glasses and sort of look at the reflection, you'll see sort of often a bluish hue when the AR coating isn't perfect because the AR coating works a little bit less in the blue wavelength than in others. So that's anti-reflection coating. That's destructive interference. Now, optical coherence tomography also uses interference and coherent light. That is, it uses interference to detect a change in the coherence of light as it passes through the eyes. Because when you bounce light off and through the retina, those waves of light are going to be slowed down different amounts depending on the nature of the tissue that they're passing through. So in the OCT machine, you have a source of light. It's bounced off the back of the eye and then goes back to a detector or to an interferometer. You also have the other light bounces off a scanning mirror, and that hasn't passed through any tissue. So then you compare the phase of those two different waves as they come back, and if they're exactly in phase, that's one thing, but if they're off by a little bit, that's built into an image, and that is what optical coherence tomography is. So OCT uses interference to detect changes in coherence of light as it passes through the eye. So we've talked now so far about polarization and about interference, constructive and destructive. And next comes diffraction. Diffraction is what happens when light encounters an obstruction or aperture, when it passes through a little aperture. And diffraction can limit the best resolution of an optical system. If we have light passing through this little pinhole, what's going to happen is it spreads a little bit as it goes through the pinhole, like so. That's diffraction. And so if we look at this image, and it's of 3 dots of light that are focused onto a screen. And you see the bottom one seems to be the sharpest image. Now, intuitively, because we work with pinhole occluders in ophthalmology, you might think that this is the image that goes through the smallest pinhole. But in fact, it's the top image that went through the smallest pinhole, because the very tiny pinhole caused diffraction, causes the light to spread out, which reduces the resolution of the system. Now, so then you might ask, well, how does a pinhole occluder work in the first place then if it makes it worse? And what a pinhole occluder has to do is it balances this effectiveness. So if the job of the pinhole is to shrink the size of the blur circle on the eye down to make it smaller. So if that does work to a point. So if the pinhole is too big, it's not going to shrink the blur circle. As it shrinks smaller, you're going to get the blur circle is going to shrink more and more. But eventually you get diffraction so that the image is going to spread out again. And so if the pinhole occluder is 1.2 millimeters in size, it turns out, if you do the math, then that seems to give the best balance of the two. A small pupil can also cause diffraction. And so you begin to get a degradation of visual acuity when the pupil size is less than 2.5 millimeters. That's what it says in the books. I think clinically it's probably not really a clinically important factor until the pupil is closer to 1 millimeter. But if you do the studies and read the books, 2.5 millimeters seems to be the number where diffraction matters. So we've done polarization, we've done interference, constructive and destructive, we've done diffraction, and then there's scattering. Scattering is what happens when light interacts with particles of a similar wavelength. Now, in general, blue scatters more, such that a shorter wavelength light is going to have higher degrees of scattering. And this matters when we're looking at the blue sky, as I'll show in a minute. If you get wider and more irregular spacing of particles, then all visible wavelengths get scattered. And that's where clouds come, and that's where corneal edema comes when the corneal fibers are irregularly spaced. Then light scatters, and you end up with a white cornea instead of a clear cornea. Same with the clouds in the blue sky. And scattering, as I said, is responsible for why the sky is blue, from one of my favorite scientific resources, the USA Today. You see, if we didn't have sky, then when we looked up into the sky, we'd just see blackness. We wouldn't see any blue light coming into our eyes. But that blue light coming from the sky, it hits the air, the blue light scatters, and then it comes into our eyes. Now at sunset, the light from the sun is passing through more atmosphere, so not only is the blue scattered, but also the yellow and only the lazy, long red wavelengths make it all the way to our eye, so that's why the sky looks red at night. Now, asteroid hyalosis is another example of scattering. You've probably all looked into the eye of a patient with your indirect ophthalmoscope and been greeted by this image, intense reflections. And then you can't believe that the patient can see anything, but in fact, the patient has 20/20 vision. And the reason that the vision is normal is that there are the particles, they create shadows, but the shadows are short and they don't reach all the way to the retina. And so it may reduce the light reaching the retina, but it doesn't actually interfere with the image. On the other hand, you, the examiner, you have a bright light on your indirect ophthalmoscope, and the light source from the indirect ophthalmoscope bounces off these particles, is scattered back towards you again, and that's why you can't see in. So how would you work around that if you wanted to see the retina of a patient who has this problem? Well, if there was a way to put the light source inside the retina, then that would work. And that's what fluorescein angiography essentially is. Because in fluorescein angiography, we're illuminating the eye with blue light, and then the and then the retinal vessels are emitting light in the green spectrum. So the blue gets all filtered away by an interference filter that doesn't let the blue out, but it lets the green out. And so that's what comes to the camera, or you can do fluorescein angioscopy with an indirect ophthalmoscope on your head in the same way. So that's scattering. So those are the basic principles of what we want to look at underlying what we do. We talked about polarization, orientation of light. We've talked about interference, constructive and destructive. We talked about diffraction, the way light spreads out through a little aperture. And we talked about scattering, how particles, how light waves are scattered by particles that are similar size to the light's wavelength. What I want to talk about next is the refractive index, because this is the basis behind much of what we do in clinical optics, is the fact that light changes speed when it goes from one medium to another. So imagine then that we have light and it's traveling through space or through the vacuum of air, and it encounters some clear plastic material. What's going to happen when it enters that plastic material? Well, the light is going to slow down. Okay, well, that's all very interesting. Well, not especially very interesting, but that's what happens. And that difference in speed is the refractive index. It's the speed of light in a vacuum divided by the speed of light in that material. So what happens, though, where it really gets interesting is, what if the light now approaches this material from an angle? So now we have the light coming in from an angle, like so. Well, now not only does the light slow down, but it's also bent, and it's bent towards the normal to the interface. So here's the interface, straight up and down is normal to the interface. So the light's bent towards the normal to the interface when it goes from a low to a high refractive index. And that's the basis of refraction of light. That's how lenses work, that's how prisms work, is by that change in direction that happens with a change in speed. And just to sort of think about how that could even happen, why that would matter, we'll talk about that in a second, but different materials have different refractive indices depending on how much they slow the light down. So air hardly slows the light down at all, so its refractive index is essentially equal. The speed's essentially equal to the speed of light in a vacuum, but water slows it down to a 1.33 refractive index. Cornea is similar, although those differences actually matter clinically, that second digit. Lens even more, plastic, and then there are high index materials that slow the light down by as much as 80%, still remaining clear in the process. So one way to think about what happens or how this can occur is, imagine, if you will, some soldiers who are marching on a sidewalk. And as the soldiers are marching on the sidewalk, they're going a certain speed, but there's tall grass to the side of the sidewalk. And so you see this soldier's marching straight ahead, but he's going to get slowed down by the tall grass. And then you go a little further, now this soldier gets slowed down, and a little further this soldier gets slowed down. And so you see what happens over the course is that the entire wave front, it changes direction. And that's sort of the basis of how this works. Now, it used to happen, I discovered it in another way myself, which is when I used to have this sidewalk that I'd ride my tricycle down. It was a steep hill, and there was grass on either side. And I would ride down the hill on my tricycle, and I discovered one day that if I veered off and began to enter the grass, that not only did I slow down, but the tricycle changed direction into the grass towards the normal to the interface. And then that sharp change of direction led to me tumbling over, and I still have this scar on my chin as a result. So my first encounter with the principles of optics was not a happy one. So just to review then, when we go from low to high refractive index, we're bent towards the normal to the interface. That means when we go from high to low refractive index, we go away from the normal to the interface. And you'll notice something here when you look at these two images, is the light is following the same path in both instances. It's just that going a different direction. And we're going to get back to that concept again and again later today. Now, let's look at this one on the right. So here we are, now we're going from high to low refractive index, so we're going away from the normal to the interface. what happens if we increase this angle of incidence, like so? Well, now we're even further away from the normal to the interface, and we're going to increase the angle of incidence even more, like so, and then it will increase this angle of incidence even more, and now you see we've reached this point where the light's so far away from the normal that it's actually skimming along the interface itself. That angle of incidence is called the critical angle. And for ordinary glass, it's 41 degrees. Well, that's all very interesting, but again, where it gets really interesting is what if you get to an angle that's greater than the critical angle? Once you're greater than critical angle, then none of the light can escape from this higher refractive index material. It's all reflected back inside. It's called total internal reflection. When the angle of incidence exceeds the critical angle, light is not refracted, it's reflected back into the material with the higher refractive index. This has consequences clinically in one particular place, which is gonioscopy. So in gonioscopy, we want to look into this angle of the eye. And so let's think about the life of a photon that's trying to head towards our eye. It starts here in the corner, it heads across the aqueous, and then it goes from this high refractive index aqueous to high refractive index cornea, then from high refractive index cornea to high refractive index tears, and then it goes from then it goes through a tear air interface, high refractive index to low, and you see it's greater than the critical angle. And so what happens is you have total internal reflection. So none of the light can escape, so you can't see the angle of the eye just with the naked eye. I used to try to do that and just try it sometime. Just look over at the angle. You can't see. But if you put a gonio lens on, then you replace the tear air interface with a tear goniosol plastic interface. They're all high refractive index materials, so the light's going to pass through. Then you put a mirror here, and then you have the high to low refractive index happens up here, where it's no longer greater than the critical angle. And so as a result, the light comes out into your eye. So gonioscopy was actually invented when with a patient who had a very steep cornea from a corneal, congenital corneal problem where the cornea was very steep, and then it became possible to look into the angle. Fiber optics is another place where total internal reflection is used. The light, again, passes along this fiber optic cable, always greater than critical, greater than the critical angle, so none of the lights escape. It's 99.99 something percent efficient transmission of light with no loss occurring thanks to total internal reflection. So that's refraction of light and refractive index. And now what we want to do is to talk about how light can be focused to form images and what vergence of light is. So we'll define vergence, we'll talk about the lens formula, real and virtual images, and the refracting power of a spherical surface. So vergence is a very important concept that we use in ophthalmic optics, and it's a measure of the spreading or coming together of a bundle of light rays coming from or heading to a single point. Now we have to specify the direction of light travel in order to know whether it's coming together or spreading apart. And in general, throughout the course of the day, unless I say otherwise, we'll assume that light is traveling from left to right across the screen. So that means that these rays of light are converging rays. They have plus vergence. These rays, on the other hand, are diverging. They have minus vergence. And these rays of light are parallel, and we say that they have zero vergence. So how do we express this vergence? How do we put a number on how much the rays are converging or diverging? It's not a matter of angles. It's really defined by where do they finally come together. Because at that point where the light rays come together, that's where an image is formed. That's where an object is located, at that point of intersection. So we define the vergence by the distance from the point of intersection. We take that distance, take a reciprocal of it, and that's a diopter. So a diopter is the reciprocal of the distance in meters to the point where light rays would intersect. So let's look at some rays of light then. And they're coming together from some source, and they reach some point of intersection here, and then they diverge again across as they go from left to right. So what's the vergence of this light? So I'm going to just come over here for a second. So here we have the rays of light are coming together. And right now over here, we're 1 meter away from the point of intersection. So we take 1 divided by 1 meter is 1 diopter. Now we're going to move closer, and now we're a half a meter away. And so the distance to the point of its intersection is half a meter, so 1 divided by a half meter is 2 diopters. And now we get closer, and 1 divided by a quarter meter is a quarter diopter. And right here, we're a millionth of a meter away, so it's 1,000,000 diopters of plus vergence. And then finally, at the point of intersection, it's infinite vergence. Then we get past the point of intersection, and now we're going to have negative because it's diverging light. There's infinite vergence. Now it's quarter of a meter away, minus 4 diopters, minus 2 diopters, minus 1 diopters, minus a half diopter, et cetera, et cetera, et cetera. So, I'm over here somewhere is, probably a tenth of a diopter away. So, that's interesting. Hang on 1 second. We don't need to be online. We don't need to take any calls from Skype. During our, all right. So now what does a lens do? A lens changes the vergence of light, and we define lens power in terms of the vergence. So here we have a plus lens, and it takes parallel rays and gives plus vergence. A minus lens is going to cause divergence of light or add minus vergence to a lens. And then finally, how do we put a number on the power of the lens? Well, it's how much it changes the vergence of light. And so we end up then with the basic lens formula of U, the vergence of light entering a lens, plus D, the vergence added by the lens, equals V, the vergence of light leaving the lens. It's our basic lens formula. U plus D equals V. Let's look at an example where we apply that formula to figure out where an image is located. So we have an object, it's 2 meters away from a lens. The lens is a +2 lens, and where is the image? So we look at this and we want to know what's the vergence of light entering the lens. So it's going to be 1 divided by 2 meters is 0.5 diopters, but it's minus 0.5 because it's diverging. And this is where I will remind you of my first rule of optics. And my first rule of optics is, when in doubt, take a reciprocal. So here we are, faced with these numbers, and you're not really sure what to do. Well, just start taking reciprocals of things, and eventually it'll make sense. So, 1 over 2, this doesn't. 1 over 2 meters, that's 0.5 diopters. Yes, that's the vergence of light entering the lens, and it's minus 0.5. So then U plus D equals V. Negative 0.5 plus 2 equals positive 1.5. So we know it's plus vergence emerging from the lens. So it's converging rays of light coming out. So somewhere, there's an image formed somewhere to the right of this lens. How far away is it? Take a reciprocal. 1 over 1.5 diopters is 0.67 meters, and so the image is 0.67 meters to the right of the lens. Now, if we have 2 lenses in a row, you can still solve this. You just have to take the image of the first lens, and that becomes the object of the second lens. So let's work through this. So we have an object. It's 10 centimeters away from a minus 10 lens. So what's the vergence entering? It's 1 over 10 diopter. It's 1 over 10 centimeters. No, it's 1 over 0.1 meters is 10 diopters. So then U plus D equals V. Negative 10 plus 10 is negative 20. So that means it's diverging rays of light coming out of this first lens. Where over to the right of this lens? So we have diverging rays of light coming out of this side. So where do these form a point of intersection? Nowhere over here. We can go all the way to the other side of San Antonio. So what we have to do is we create imaginary extensions of the rays of light back to a point of intersection on the other side of the lens. How far away is it? Take a reciprocal. 1 over negative 20 diopters is 0.05 meters or 5 centimeters away. So the image of the first lens becomes the object of the second lens. So now the first, and so this image is 5 plus 20 away, so 25 centimeters. 1 over 0.25 meters is negative 4 diopters. U plus D equals V. So it's plus 4 coming out. Converging rays of light, how far away is it? Take a reciprocal. 1 over 4 diopters is 0.25 meters or 25 centimeters away. So the image of the two lens system is 25 plus 20 plus 10 centimeters away from the object. So now at this point, I could sit up here all day and I could do 50 more examples like this, and you won't get anything more out of this of the lecture, because at some point you have to do it yourself. It's sort of like, if you ride with a friend to work every day, you might go every day for a year in the same car, follow the same pathway, but you're never driving. And then one day the friend's sick and you borrow the car and it's your turn to drive, and you get to the first intersection, you don't even know which way to turn. So you have to have your hands on and to do some of these yourself to work through. So that's one of the reasons that Connie West and I put that book together, put our book together. There are other books like it, just so you can work through some of these on your own. And that's true of all these kind of calculation type questions that come up. So now, what I want to talk about next is the object and image space and what's real and what's virtual in terms of objects and images. So it's always true when we look at a system like this that the incoming rays are the object rays. They define the object. And the outgoing rays are the image rays. They define the image. But where's the object itself? Well, it depends. A real object is located on the same side of its rays, a real image on the same side of its rays, whereas a virtual object and an image are formed on the opposite sides of their rays, found by drawing imaginary rays of extension back to the point of intersection on the other side of the lens. So if we look at an example here, here's the object. You see it's on the same side of the rays that define it, so it's a real object. It creates an image. It's also on the same side. That's a real image. Again, here's a real object, but here's another example where it's diverging light. No image over here. We create imaginary extensions of ray of light back to a point of intersection on the other side of the lens. That's a virtual image. And we can look at other examples like that where when you see the dotted lines, we're creating imaginary extensions to form virtual objects. So how is it then that some curved high refractive index material can change the vergence of light? Well, what it has to do is the refracting power of a spherical surface. And it has to do with the curvature of the lens and its refractive index. So if we have some unknown material, such as shown here in a lens, and we have two different refractive indices, n prime and m, that difference in refractive index is going to determine how strong the lens is as the light encounters it. The other thing that's going to matter is the curvature, which is r, the radius of curvature. The more curved the lens is, you would imagine, the stronger the lens. But what you might not imagine is that the bigger the difference in refractive index, the stronger the lens. This can be broken down into an equation. The refracting power of a surface is n prime minus n divided by r. And this is one of these equations that to me is almost like poetry, because it takes a lot of different concepts or thoughts or observations and puts them by positioning the letters in just the right way. It tells a whole story about how things work. So again, as I say, having the r on the bottom, the smaller number on the bottom makes for a bigger d. Well, the smaller r means a more curved lens, and you know that intuitively. The more curved the lens, the stronger the power. This one's a little less intuitive, but let's think about it. If we had I could tell you that I could take a lens made of plastic, and if I were to plunge that lens into liquid plastic of exactly the same refractive index, it's not going to have any power at all. It'll just disappear. Or I could even tell you I'm holding in my hand here a lens that's made out of air, but it doesn't have any power right now because the lens made of air is surrounded by air. But if I were to put an air bubble in water, now that's going to have refractive power. So now the only question that this leaves behind is it a plus lens or is it a minus lens? And there are formulas you can see in books where you have to keep track and you put a negative sign here, and you have to keep track of which n is on which side. But rather than do that, there's a simpler and more intuitive way to figure out if it's a plus or minus lens. You have this curved surface, that's a refractive interface. You draw a rectangle around it, and now you get out your Crayolas, and you color in the side that has the higher refractive index. In this case, if n prime is the higher refractive index, then it's going to be a minus lens. Whereas if n has the higher refractive index, you'd color in this side, and it would be a plus lens power. The refractive index of cornea is 1.37, and the refractive index of aqueous is 1.33, so we would color in the side, the 1.37 side, and see that that looks like a minus lens, which it is. So the back surface of the cornea has a power of 5.7 diopters, but it's negative 5.7 diopters. Now, we can also figure out the front surface of the cornea. For the purposes of this example, I'm going to continue to use the radius of curvature of 7 millimeters. But now, n prime minus n on the front surface of the cornea, you have air cornea interface. So it's 1.37 minus 1 over 0.007. So that's 52.9 diopters. So the front surface of the cornea, in this example, is plus 52.7 diopters, 52.9 diopters. You subtract the 5.7 off the back, and you get a corneal power overall of roughly 48 diopters, which is about right. Now, why is it, though, when we open our eyes underwater, you can hardly see anything. You can't see your hand in front of your face, barely. Why is that? Well, let's do the math. What we've done is we've replaced the 1.00 of air with 1.33 of water on the front of the cornea now. So the power of the front of the cornea changes from 52.9 diopters down to 5.7 diopters. And then we subtract the minus 5.7 diopters off the back of the cornea. So when you open up your eyes underwater, it's as if you've had your cornea removed. You're a 50 diopter hyperope. No wonder you can't see that much. So why is it then, when we put on goggles, do those goggles, we can see better? Do those have 50 diopter lenses in them? No 50 diopter lenses in there. They simply restore the normal air-cornea interface. The difference in refractive index between the air and the cornea is restored. And so, as a result, this means that any lens is going to have a different power when we immerse it in fluid. And here in ophthalmology, we take intraocular lenses. They might have one power out in air. They're going to have a different power when you put them inside the eye because they're going to be in the fluid of the eye. We like to be able to calculate that difference. So I have an example here. And there's an example in your notes which is slightly different. And throughout, actually, in the handout, which will also be made available to viewers at home, in the handout, there are some examples, simple examples you can work through as well. So the plus 20 diopter intraocular lens, if it's marked as plus 20, what's the actual power of the lens in air? We can figure that out. We have to use this formula. It's a ratio of the exact formula that I just explained to you, d equals n prime minus n over r, but you just take that and you divide it by d equals n prime minus n over r in the aqueous as well, and you just end up with this relationship. R goes away, which makes perfect sense because the radius isn't going to change when you're outside of, when you're in air versus water, the radius doesn't change. So again, the poetry of the equation is that the r goes away because r no longer matters when you're comparing in and out of water. All you care about is the ratio of the difference in refractive index. So we plug in the numbers then, air 1.49, plastic is 1.49, air is 1.00, aqueous is 1.33, and we know the power in aqueous is 20, we don't know the power in air, but we just do the subtraction, you cross multiply, solve it for D, and you end up with 61 diopters. So that 20 diopter IOL says 20 diopters right on the box. If you were to measure it in a lens meter, you'd find that it's a 60 diopter lens in air. So then finally, or in this section, we want to talk about lenses and ray tracing. Not finally, the next step in this section is lenses and ray tracing. And you see I've carefully synchronized the Roman numerals in the slides with the Roman numerals in your handout. It used to be my handouts were off slightly from the from the lecture, but I fixed that all up. But it used to be that all of a sudden it would sound like one of those boards in the train station, because you'd hear when I would go off the notes. But I think that we're purely on the notes today. So lenses and ray tracing, we're going to talk about focal points, focal planes, and focal lengths, the central ray, and then we're going to work our way towards understanding. All of this is to help us understand basically how the eye works. What are the optics of the eye? So to get there, let's first start with focal points. Each lens has two focal points, anterior on the incoming ray side, posterior on the outgoing ray side. We also sometimes call them primary and secondary focal points. The primary focal point is the point along the optical axis where an object must be placed for parallel rays to emerge from the lens. So here's a lens. The focal point is going to be here, because if we put an object here, the rays of light that emerge from the lens are parallel. For this minus lens, it's a little more complicated. We have to have a virtual focal point over here so that the converging rays come in and they end up leaving parallel. So those are the primary focal points of those lenses. Now you can have a focal point, but there's actually anywhere on a plane that you could put an image and have parallel rays come out. So you actually have a primary focal plane, because whether the light's here or anywhere on this plane, they're going to emerge as parallel rays of light. Okay, that's all well and good. Now we also have a secondary focal point. The secondary focal point is the point along the optical axis where parallel incident rays are brought to focus. So, we used to take a magnifying glass and take the rays of the light from the sun and try to burn ants with our magnifying glass. That was what you were doing. This was a positive experience in optics for me in a young age, was finding the secondary focal point of that lens. And when you got it just right, then the ant would burst into flames. It was positive for me. It wasn't positive for the ant. So the focal length is just the distance from the ideal lens to its focal point. And it's the reciprocal of the power of the lens in meters. Oh, there we are, taking a reciprocal again. So the focal length is 1 over the power of the lens in diopters. Well, so if you have a 20 diopter lens and you want to burn an ant with your 20 diopter lens, you're going to hold it 1 divided by 20 meters, or 0.05, 1 over 20 diopters is 0.05 meters, or 5 centimeters away, which, by the way, is about how far we hold the indirect ophthalmoscope lens from the eye when we're examining patients, or when we're treating patients with laser, for that matter, laser indirect ophthalmoscope. It brings us all back to those, when we're burning ants, because instead we're zapping bad blood vessels with a 3 diopter lens is going to be a 33 centimeter lens, or et cetera. So when I talk to the physics people in the lab, if I tell them I want a 20 we need a 20 diopter lens, they have no idea what that means. But if I say, oh, that's a 50 millimeter lens, now that makes sense. So the next step in understanding how these is to talk about ray tracing. And a key part of ray tracing is something called the central ray. So far when I've shown you examples of objects and images, we've assumed the object is a certain point. But now we're going to give the object some extra axial extension, like so. And so we want to draw a central ray which goes from the tip of the object through the center of the lens, like so. And what that central ray tells you is it's going to tell you where the image is, if it's upright or inverted, and also help you understand if it's magnified or minified. Here's another lens system. So let's say we have our object, we drew a central ray. Now we do U plus D equals V like we did earlier today, and it tells us that the image is going to go here. Well, we know that then we draw a line from the image location to the central ray. So you see that in this lens system, the image is going to be inverted. Let's look at another example. Here's an object. We have a minus lens. We draw a central ray from the tip of the object through the center of the lens. We do our U plus D equals V calculation. Turns out that the image in this case is over here to the left. And so we draw our line up to the central ray. So now in this case, you see the image is upright and magnified, and it's thanks to the central ray. Now you can take ray tracing to another level, and some of the clinical optics books do. You can draw 3 rays one through the primary focal point, one through the secondary focal point, and a central ray. And you can use that to determine where the image is without doing any math. But I find that to be a little confusing, and so my preference is draw the central ray, then use U plus D equals V to find the image, and we know that the image is going to go to the central ray. So that for any lens of any particular power, we're going to have the central ray tells us where all the possible images might be, depending on the power of the lens. The corresponding points of the objects and images must always fall on the central ray. And with multiple lens systems, again, the object of the first lens becomes the image of the second. The image of the first lens becomes the object of the central lens, second lens. So here's the same example I showed you earlier, but now we draw our central ray. We do U plus D equals V. It shows us the images here. So now this becomes the object of the second lens. So now we draw a tip of this object through the center of this lens. That's our second central ray. Do U plus D equals V again. It tells us that the image, we remember, is over here. And so that's our final image. So the final image is inverted and minified compared with the original object. You can measure it on the page. So as I mentioned before, we can do a combination of, you can either do U plus D equals V plus the central ray, or you can do ray tracing to find the image, size, orientation, and location. So next I want to talk about thick lenses, because so far all I've mentioned is the ideal thin lens, which has these two focal points and the lens itself. But a thick lens is more complicated than that. It has 6 cardinal points. It has 2 principal points, which we usually call principal planes, 2 nodal points, and 2 focal points. So, here's a lens, the diagram of a thick lens. And so you see, instead of just one point here, we have these 2 principal planes, and we have the 2 nodal points. So if we want to draw our central ray, we still go from the tip of the object, but now we go into the first nodal point. Then the light just jumps magically to the second nodal point and continues on at the same angle as it went in. So that's one difference. And the other difference is these principal planes, when you're measuring, doing U plus D equals V, you're doing this with respect to these planes rather than with respect to the center of the lens. So those are the modifications that we do when we have a thick lens to account for the thickness of the lens. Now there's one other interesting thing to discuss, and that is what happens if you have air on one side but material of some other refractive index on the other side of a lens. What happens is the nodal points get pulled into the side with the higher refractive index, like so. So the nodal points are pulled into this side. Now, why is that exactly? Well, again, I'm not exactly sure I understand either, but that's why I say it happens magically, which is, really should be a perfectly satisfactory explanation. And this is where, even though I have the engineering background and even though I did some of the optics stuff, in residency, I really didn't, a lot of this stuff was a mystery to me too. And so if you were to just, get me and start probing me just to scratch the surface to find out more behind what I say, you may or may not find content behind the surface of what I'm presenting. Notice I don't take questions. No, I do after class. So the nodal point is pulled into the side of higher refractive index. Well, that's all very interesting, you say. Why do we need to know where in the world would we have a lens that has air on one side and water on the other side? That's not a very natural thing. Well, what about the eye? And Goldstrand, in fact, an ophthalmologist who worked out the optics of the eye itself. And you'll see some familiar things here. You see we have 2 principal planes. We have 2 nodal points that are pulled into the side with the higher refractive index. And then we have a focal point, the secondary focal point here on the retina, primary focal point over here somewhere. So Goldstrand was the only ophthalmologist ever to win a Nobel Prize yet for working out this, the math and the optics of this. But we're not trying to get a Nobel Prize. We just want to understand a little bit how the eye works. So for us, we'll take the reduced schematic eye. So the reduced schematic eye, the numbers are sort of rounded. So the power is 60 diopters, and the index of refraction inside is an even 1.33. The two principal planes here are close enough together we can say that there's one and that they fall right on the surface of the cornea like that. And the two nodal points are close enough together we can say one. But this distance from the principal plane to the nodal point, we can't ignore that, so we keep that. And that turns out to be 5.5 millimeters. So the axial length of this schematic eye is 22.5 millimeters, and this distance from the nodal point to this focal point happens to be the reciprocal of 60 diopters, or 17 millimeters. So what do we use that for? Two things that we use the reduced schematic eye for. One is when we're figuring out magnification of the eye, and we'll use this 60 diopter number. And the other is to figure out image size on the retina, and we'll use this 17 millimeter number for that. So let's look at an example. Before we look at the example, just a quick reminder of similar triangles. That's used when two triangles have shared angles like so, then the ratio of A to B is equal to the ratio of X to Y. All right, so on to our example. What is the diameter of the blind spot when projected 2 meters from the eye? Now we assume the optic disc has a diameter of 1.7 millimeters. So that's the blind spot, 1.7 millimeters on the retina. How big is the 1.7 millimeters when we project it 2 meters away from the eye? Well, you see, it's a case of drawing a central ray from the tip of the optic disc through the nodal point and off into space, and then this other axial line. And then we end up with, we know all the numbers then. We have similar triangles where we know all the numbers but one. We know 1.7 millimeters, 17, and we know this is 2 meters away plus the 5.5 to the nodal point. So we draw that as similar triangles, like so. The only one we don't know is the height, but you do 1.7 over 17 equals x over 2005, and the result is 200 millimeters or 20 centimeters. So the blind spot in space is 20 centimeters in diameter when projected 2 meters from the eye. That's pretty substantial. Finally, I want to talk about conjugacy of light and points and planes of light. That is, so far we've talked about light traveling from left to right. We have an object and an image. We do our U plus D equals V. We do our central ray. There's the optical system. What happens if we turn the light around? If we turn the light around, the object becomes the image becomes the object. And another way to say this is that these points, the tip of the object and the tip of the image, they're optically conjugate. They're optically in the same place. So an example of that is when you're looking at this slide. Right now, you know that there's an image of this slide on your retina. But what that means through the principle of autoconjugacy or optical conjugacy is there's also then an image of your retina up on this slide. And so you can't see it though because there's no light source inside of your eye. But if we were to take a volunteer, so right now there's an image of this retina on your retina. And if we were to take a little fiber optic light source and punch it into your eye and turn the room lights down, we would see an image of your retina up here on the screen. They're optically conjugate. In fact, there's an image of each person in the audience. There's an image of each one of your retinas dancing up here on the screen. They're optically conjugate. The direct ophthalmoscope. When you're doing direct ophthalmoscopy, you're looking at an image of the patient's eye, so there's an image of the patient's retina on your retina, but there's also an image of your retina on the patient's retina. It's just the patient can't see it because the photons are all going in one direction. And then in indirect ophthalmoscopy, it's a little bit more complicated because there we have an intermediate aerial image of the retina that's right about here in this picture from Dave Guyton's lecture. So there are actually 3 conjugate planes. There's the aerial image of the retina, the patient's retina, and the examiner's retina. All 3 are optically conjugate. And it was actually when giving this lecture that Dave Guyton Minkowski had a discussion, and they realized that if you put an eye chart right here, then the eye chart, Guyton already realized, if you put a pen here, the pen is on the image of the retina, therefore it's focused on the retina. So that means why not a pen, why not an eye chart? So you could put an eye chart and have the eye chart focused on the retina independent of the optical performance of the eye. That means a patient with cataract would still be able to see the eye chart clearly even though their lens isn't doing a good job of forming an image. And that was the basis of the Guyton-Minkowski potential acuity meter, which was used for years to determine which patients who are having cataract surgery could potentially what the potential was for their vision after the cataract surgery. I think once insurance stopped paying extra for the potential acuity test, though, it sort of stopped being done. But it worked well. So those then are the basics of part one. We've talked about physical optics. We've talked about vergence. We've talked about lenses and how they work. And so this is then the end of part one. And we'll be moving next to part two, which is to talk about refraction in particular. Now into part two. And for part two, we're going to talk about visual acuity testing and refractive error. And then we'll work into correcting refractive error with glasses, contact lenses, intraocular lenses, and refractive surgery. So for visual acuity testing, we want to know a little bit about visual angle, the different types of visual acuity, near vision, how to test vision in children, the types of eye charts, and we'll review what causes legal blindness. Or not what causes it, but what defines it. And before we talk about visual acuity, just one more review of some basic geometry, which is that we all know that a degree is 1/360th of a circle. But then if you blow up a degree and break it up into 60 pieces, then that's 1 minute of arc. And if you take 1 minute of arc and break that up into 60 pieces, that's 1 second of arc. So 1 second of arc is 1/60th of a 60th of a degree, or 1/3600th of a degree is a second of arc. What are the types of visual acuity? There are 3 types. There's minimum visible, minimum resolvable, and Vernier acuity. Minimum visible acuity is just your ability to see a spot on the wall without necessarily defining what that spot is. And your resolution of the resolving power of the eye for just seeing a dot of dirt on the wall is 10 seconds of arc. Minimum resolvable acuity, that is your ability to recognize a letter, to tell that an E is an E and not something else, is 1 minute of arc, or 60 seconds of arc. So to see a 20/20 you have to have 60 seconds of arc. And then Vernier acuity is your ability to see a break in a line. So this may project differently to different parts of the room, but you see on the right side, these lines have a break in them. And your ability to perceive that break, that's your Vernier acuity. And Vernier acuity is the resolving power there is 2 to 3 seconds of arc. Not 2 to 3 minutes, 2 to 3 seconds of arc. That's finer, that's less than the separation of photoreceptors in your retina. It's exquisitely sensitive, and it's the kind of visual acuity that's used then when adjusting an instrument. For example, you turn a knob until the 2 lines exactly line up, because that's using your Vernier acuity to find that endpoint. In old manual focus cameras, they had a split screen focus, and that split screen was because it was using your Vernier acuity to get that last little bit of resolution. How can it be that you can see with more resolution than the separation of your photoreceptors? Well, it probably has something to do with the ganglion cells and the other cells in the retina that do computations that figure out this angle, and they anticipate that the angle should be a certain amount, and by averaging over space, it can do that, make that decision. What are the dimensions of a of the letter E that's used to measure vision? Well, a 20/20 is 8.73 millimeters tall. Each leg is 1.75 millimeters tall. But more importantly, a 20/20 subtends 5 minutes of visual angle, with each leg subtending 1 minute of visual angle. Because again, remember, we said the resolving power of a 20/20 is 1 minute of arc. So that's how you can see those different legs. Now, as a result, if a 20/20 subtends 5 minutes of visual angle, a 2200 subtends 10 times that, or 50 minutes of visual angle. And what that means is something that you know intuitively as well, is a patient with 2200 visual acuity, for example, can't read the 20/20 line. They can read it if they stand 2 feet away, because 2/20 vision is the same as 20/200 vision. It's all a matter of the angles of light and the resolving power of the eye. So what happens then if you have a patient who cannot see a standard Snellen visual acuity chart? Well, you move the patient and the chart closer together, so that a 20/30 optotype at 5 feet is going to be 5/30 vision, which is 5/30 is the same as 20/120. Now, if you'd had a normal, if you had just had the patient at standard distance, they would have seen the 2200 letter, but they wouldn't have seen the 2100 letter, so you would have said they have 2200 vision, but in fact they have 20/120 vision. If you can't record, no matter how close you move the patient, then you have to use other methods, such as counting fingers and hand motion, more qualitative assessments of visual acuity. But usually you can get a big enough eye chart that's close enough to get some measurement, if they have it. For near vision, we use reduced Snellen acuity or a Jaeger type or a point type with a near reading card. What's key here is that it has to be at a noted distance. That is, these cards are defined to be used at a certain distance. And you can get big errors if you don't control that. So if you think about if an eye chart's 20 feet away and the patient leans forward a little bit or back a little bit, well, you might get a little bit of error. But if an eye chart is supposed to be held 28 inches away and they're actually holding it 14 inches away, or if it's supposed to be held 14 inches away and they're holding it 7 inches away, then you're going to get big errors in visual acuity. And I once had a patient referred to me for possible malingering because she had 100 vision at distance, but 20/20 vision at near. And I went through this thumb screw visual acuity where Simmons Lascelles calls it a thumb screw visual acuity. You start them at 20/15 and you say, can you see any of the letters? And say, no, I can't see any. Well, do you see the dots? No, I don't see any dots. And so then, okay, I'll show you the bigger ones. And you show the 20/20, and they still ask them, and they still can't see them. And say, okay, I'm going to show you the bigger ones. And you show the 20/25 letter. And, you don't see any dots or anything? No, I can't see them. So I'll show you the really big ones. And usually most kids who are faking it will give in by 20/25 or so. But at this one, we marched all the way up to 2100. And that was the one that she could see. And then I moved her half the distance to the eye chart, and she was able to see the 20/50 line. And I thought, well, that's pretty good, because some of the residents have trouble figuring out which ones she'd be able to see, so I doubt that she'd be able to figure it out on her own. And then I had her read the near, because 10/50 is 20/100, you see, so it all worked. So then I gave her the near card, and she held it 5 centimeters from her face and read the 20/20 line. And so that was, once we held it at the proper distance, it was 2100. She ended up she wasn't faking it, she had just early Stargardt's, and later that was confirmed. So that's visual acuity in adults, and then in children, I wanted to at least mention testing visual acuity in kids, and just remember there's only one thing you really need to know about babies: they can smell fear. So when working on testing visual acuity in kids, the first thing to think about is not to let the child know that you're scared. That you need to somehow get information out of this creature, this alien space creature, and find out whether or not he can see. So what do we do? Well, first, just an aside, we do want to be sure that the eye is properly occluded with a good patch. If you try to use a cover like this, as soon as you turn your back on them for a second to point at the letter, the cover comes away and they're gonna peak. But here in this case, an actual case of mine is a patient who I couldn't do retinoscopy or anything in this eye, but yet in the page it said she had 20/20 vision. And you see she had a patch on, but she was squeezing and turning her head so she could peek. So you have to be a strict disciplinarian and have them sit up straight and hold their head straight and put the patch on their eye and push it down on the nose so that they're not peeking when you have them have them read. And actually I should say that again, although I do have a background in some engineering background, et cetera, I do actually take care of live patients. I take care of kids and adults with strabismus, and I do refractions, and so I have some clinical experience that I bring to bear on this. Objection to occlusion, of course, is not a quantifiable way, but here he's crying. I mean, here he's fine with the patch over one eye. You put it over the other eye, and the hat comes off, and he's lying on the ground, and he's crying. So you have to worry that maybe he has poor vision in that eye, or maybe in this case you put this funny patch on, poking him in the eye, but because he ended up having fine vision in both eyes. So, and then now one of the earliest things that we can see is optokinetic nystagmus, some response to a moving target. So you can use the OKN drum, for example, and look for that movement of the eye in response to a moving target. This, for those of you who are confused, this is the OKN drum, and this is the patient. Then we just look at fixation and following, the ability to track. Again, it's not quantitative, but we can check that. A baby's not going to have fixation and following vision. You can just say blinks to light or something to that, or pupils react, but that's all. It's not till older that they'll fixate on a target and track it. Here's one of the earliest ways that we can get some quantifiable visual acuity was with teller acuity cards. There's a person behind that peephole there, and they're deciding whether the baby's looking at this side or this side. And if it matches, if the baby looks towards the stripes and you use smaller and smaller stripes, then you can say that they have that level of visual acuity. Now finally, as they get older, we can get them into picture optotypes, whether the Allen cards or the Leia symbols, and get some Snellen equivalent, which may not be exact, but at least you can compare the left and the right eyes to look for amblyopia. And then letter optotypes. We used to use the tumbling E, but kids would get confused with left and right vision, so now we've gone to the HOTV letters because he doesn't have to know his letters, but he can just match, and that gives us a true Snellen equivalent, much closer to Snellen equivalent. In amblyopic eyes, we do have to be careful to you can't just have them read isolated letters or you'll get a false reading on your visual acuity, so you need either use a line of letters or crowding bars. Either one works fine. So to summarize then, visual acuity responses during life. At birth, you get a pupillary light reflex or blinks to light, and that's about all you can say for the patient. OKN begins to come in fairly early in life, should be there by 6 weeks. Following movements and fixation are more like, should come in, begin to come in as early as a month of age, but you don't get too excited until they're about 3 months old, and you see that. So in summary, to test visual acuity in pre-literate children, we look at blink to light, OKN, fixation and following, or central steady maintain, the preferential looking tests, and then finally into picture optotypes, such as Allen figures or the Leia symbols, HOTV, and then and also you can use the illiterate E game, or the Landolt C is used in Europe. Then finally, there's also visually evoked potential testing, which is the only one of all these methods that doesn't require a motor response on the part of the child. In illiterate adults, you'd use the same. This is one of those questions that you know the answer, but you might forget the answer if you're actually asked out of the context of having a patient in front of you. You would use any technique that you use with a child, or you could also have them read the numbers. And this is something we'll touch on a little bit more later, but factors other than disease that can reduce measured visual acuity. That is, so a patient might just need a refraction. And now that may sound obvious because you can test pinhole acuity, but say you've already done your refraction and the patient still can't see. Well, now you can test pinhole acuity above and beyond that to see if the patient needs a refraction. A small pupil we've already mentioned because of diffraction can reduce visual acuity. A very large pupil can also reduce visual acuity by uncovering certain aberrations in the eye. Decreased contrast of the eye chart could also reduce the measured visual acuity. Very young patients don't have 20/20 vision, and you don't expect that till age 5 or 6. And then very old patients without other disease may or may not get the smallest letters on the eye chart. And then the definition of legal blindness in the United States, best corrected vision has to be 2200 or worse, or the field of vision in the better eye is 20 degrees or less. And that doesn't vary by state, so it's a federal definition that you might be expected to know. State driver's license requirements do vary, so it's not something that you're necessarily expected to know for a national exam. And what is the ETDRS acuity chart, and why is it used in large studies that use visual acuity as an outcome? Well, the ETDRS, or Early Treatment for Diabetic Retinopathy study chart, has letters that are of equal viewing difficulty, as opposed to the Snellen chart, which has some are easier and some are harder to see. Each line has 5 letters, which isn't true of this Snellen chart. The spacing between the letters is equal to the letter size on that line. Again, not true here. And the optotypes change in 0.1 log unit increments, so that a 3-line change is a doubling or halving of the visual angle. That way, if a patient goes from the top line to 3 lines down, that's 3-line improvement is the same as a different patient who goes from, say, this middle line to 3 lines below that. Both patients would be considered to have the same outcome, so that's why it's can be used in larger studies. So next I want to talk about refractive error, defining it, talk about far points and focal points, how we correct refractive error, and the role of lens effectivity, that is the position of lens in front of the eye. So refractive error, if we go back to the model eye that we talked about earlier this morning, remember how the secondary focal point was on the retina of the model eye? So if the secondary focal point is on the retina, then the patient is ametropic. They have no refractive error if that occurs with accommodation relaxed. On the other hand, if the focal point doesn't fall on the retina, it might fall in front, in which case you have myopia, or behind, in which case you have hyperopia. Why would the focal point fall in front of the retina? Well, either the eye is too strong or it's too long. Either case leads to focal point in front of the retina, whereas in hyperopia, the eye is either too short, axial hyperopia, or it's too weak, there's not enough power. In either case, then the focal point's behind the retina. There you go. Now, there's another way to consider refractive error, and that's by far point. And we get that by turning the light around and seeing what happens to light as we project it through the optics of the eye, trace the rays. So here's an emetropic eye. We start here in the retina and trace backwards through the optics of the eye. And since this is at the focal point, it's now the primary focal point, since we turn the light around, it's going to be parallel rays of light emerging from the eye. And so the far point is going to be at infinity. So the far point of an emetropic eye is at infinity, whereas if we take a myope, for example, and we trace the optics through the eye, then you see the front of the eye is too strong, or the eye is too long, but just think of it right now, the front of the eye is too strong. Then instead of parallel rays of light coming out, they're going to be converging, so there's going to be some far point somewhere in front of the eye. And that's the farthest away that the eye can see clearly without accommodating. So at least in the case of the myope. So I'm a myope, so if I were to take my glasses off, relax accommodation, then the far point of my eye is where it first comes into focus, so it's going to be somewhere right here. And you can basically take the reciprocal of that to estimate my refractive error. That's far point. So in hyperopia, we trace through the optics of the eye. Now the front of the eye is too weak, and so there's not enough power to get parallel rays of light coming out, so it's diverging rays of light. So where's the far point of this eye? Well, it's nowhere to the left here, so we must create imaginary extensions of the rays of light back to a point of intersection on the other side. We find a virtual far point that's behind the retina in hyperopia. So let's consider then the difference between far points and focal points. Both describe refractive error and both can be useful, but in different contexts. Focal points are measured from the retina and are never more than a few millimeters away. It turns out it's about 1/3 of a millimeter for each diopter of refractive error. Whereas far points are measured from the cornea and they can extend centimeters, meters, off to infinity in an emmetropic eye. And it represents the farthest away that a non-accommodating eye can see clearly. So how do we correct that ametropia? So we have a patient who has a refractive error. Well, the way I think of it is, and I'll explain why in a minute, is if you locate the far point of the eye, now you choose a lens whose focal point coincides with the far point. At that point, in that case, then you've corrected the refractive error. So for a myopic eye, here's the far point in front of the eye, and we choose a minus lens whose focal point coincides with the far point of the eye. For a hyperopic patient, you take a plus lens, and you choose a lens whose focal point coincides with the far point. The take-home message of this is that it's not just the power of the lens that matters, but it's the position of the lens in front of the face that matters when you're trying to correct refractive error. It's the power and it's the vertex distance. Both matter. So that's why we're going to talk next about lens effectivity and vertex distance of plus lenses and minus lenses. So let's take a patient. Here's a case where you have a patient who's a plus 10 hyperope. It turns out that if we move a plus lens forward away from the eye, then we get increased effective plus power. And so that you can see that in a practical sense. You might see an aphakic patient who's trying to look at something up close. You might see them drop those glasses down on their face like so, and that's going to give them more plus power. Another way to think of it is that as we move the lens forward, we need to reduce the power to maintain the same correction. Let's look at an example of that. Here we have a patient plus 10 lens. So then this is properly corrected. So we know that the far point of the eye must be 1/10 diopters or 0.1 meters or 10 centimeters away from the lens. So there's the far point. But now if we push that lens forward away from the eye, now the focal point's going to move forward too. So now the refractive error is not corrected anymore. So we have to give a weaker lens here. We have to reduce this, say, to plus 9. Now it's going to have a longer focal length because 1/9 is 0.11 meters or 11 centimeters. And now the far point, once again, coincides. So to maintain proper distance correction, you would decrease the plus power as the lens moves forward. Now there's a way that you can, there's a semi-intuitive way to help you remember this, and that is that you know that roughly an aphakic patient is going to have a spectacle lens power of, say, 10 to 12 diopters. But then if you were to put them into contact lenses, you know from your clinical experience that a contact lens patient, aphakic, is going to be like about a 15 to 18 diopter contact lens. Or an intraocular lens power is going to be, you know, clinically roughly 18 to 20 diopters for a typical aphakic patient. So by this clinical knowledge, you can sort of work out the fact that the closer you get to the retina, the more power you're going to need to correct the same refractive error. And so in this case, the optician only has one power of plus lens, but just prescribes based on vertex distance. So now this then gives us an opportunity to give you questions that you have to answer, which is to do a vertex distance correction. That is to figure out how to change the power of a lens given that it's going to move, say, from the spectacle plane to the contact lens plane or vice versa. And there's 3 steps to do that. First, you figure out the focal point of the present lens because that tells you where the far point of the eye is. Then you calculate the distance of the new lens from the far point. And then you take a reciprocal of that new distance because that's going to be the power of the new lens. So let's look at an example. So a patient comes into your office wearing a plus 12.5 diopter spectacle lenses with a vertex distance measurement of 13 millimeters.
the patient wishes to have contact lenses, what power contact lens would you likely need? Well, well, we go to the first rule of optics, which is when in doubt, take a reciprocal. And in this case, we're going to take a reciprocal of the 12.5 diopter lens, which is 0.08 meters or 8 centimeters. And yes, that tells us that the far point of the eye is 8 centimeters behind the lens, behind this lens. Now the new lens is going to be 13 millimeters closer to the far point. So here's the new lens. It's a contact lens. So we're going to subtract 80 millimeters minus 13 millimeters, and that gives us 67 millimeters. So what power lens do we need to have a focal point that falls on the far point of the eye that is a focal length of 67 millimeters? Take a reciprocal. 1 over 0.67 meters is 15 diopters. So it's just 3 steps to get to that answer. There are books and formulas that you can, so there are formulas out there that can do the correction for you, but I think it's best to just take it in step by step like this to work it out. So for minus lenses, it's kind of the same, but kind of the opposite. That is, moving a minus lens forward will decrease its effective minus power, but that's the same as adding plus power. So whereas moving a minus lens toward the eye increases the effective minus power. And this is the one place in optics where people who wear glasses have a slight advantage over those who don't when taking a test, because I remember I was taking the exam, and again, like I say, you know, this didn't come naturally to me. And so there was a question about this very topic, and so I was taking my glasses and sort of sliding them down on my face to see. And then I look around the room and I see, you know, 2 or 3 other people in glasses are going like this. And what I was seeing was less and less, you know, less minus power as I went away. Another way to remember it is that is to think of somebody, myopic patient, myopes more common, sitting on the beach, and you know their glasses are kind of down on their face, and then someone walks by that's of interest to them. What are they going to do? They push the glasses up on the nose to get that full minus correction. So next, let's go to accommodating and prescribing bifocals. We'll talk about the physical properties of accommodation, how to measure it, how to prescribe bifocals, and the different types of hyperopia. So accommodation is an increased convexity of the lens that adds plus power to the eye. We'll consider it as acting at the cornea. So in other words, here's the basic Helmholtz theory of accommodation, which is that you have some object and you have the plane of the retina and you want it to be in focus on the retina, and here's the lens. Now, notice that as we move into, up until now, we've been considering objects at infinity. That's parallel rays of light coming into the eye. Now we're considering an object closer, so it's diverging light coming into the eye. So how do you get more power? Well, the zonules are tight on the lens. They're keeping it flat. So the ciliary muscle contracts, the zonules loosen, and the lens takes up more of a round shape, so it gains more plus power, and the image moves closer, like so. So ciliary body's relaxed, the image is back there. Ciliary body contracts, the zonules relax, the lens becomes more round, the lens becomes more powerful. That's what puts the image on the retina in accommodation. So this physical ability of the lens to change shape is the accommodative amplitude of the eye. And that's one way to gain accommodation. Now, there is potentially another way to gain accommodation, which we don't use, but some animals do. And there are these accommodating intraocular lenses. And the people who invented this, they must have studied their optics, and they realized about effective lens power. If you could move the lens forward in the eye, you can get more plus power that way rather than making it rounder. So these intraocular lenses have hinges on them, and the theory is that as the ciliary muscle contracts, the vitreous pressure increases, it pushes the lens, this lens forward, and gives some extra plus power. Those are in clinical trials, and so not clear that they're working as well as expected, but it's at least a nice idea. But in most cases, what we're looking at is this change in shape of the lens to get accommodation. So how do you quantify that? Well, first of all, we've already talked about the far point, which I'll define more rigorously now, is the point on the visual axis that's conjugate to the retina, you know what that means now, with accommodation completely relaxed. The near point is the point on the visual axis that's conjugate to the retina with accommodation fully active. That's the near point. And the accommodative amplitude is what gives you that difference. So amplitude of accommodation is a number that's expressed in diopters. It's the maximal capacity of the lens to accommodate. There's one other number that we can put on accommodative ability, and that's range of accommodation. It's the distance between, it's two numbers, a near and a far distance. And it's the linear extent of clear vision obtainable using accommodation. So how do we measure accommodative amplitude? Well, we take a target and we attach it to a ruler that's scaled in centimeters and diopters, either a Prince rule shown here or a Royal Air Force rule. So there are numbers on that, not just in centimeters, but also in diopters. And then you cover one eye and you move this target closer and closer, gradually move it closer to the eye, and strongly encourage the patient to keep the target in focus until they can no longer keep it in focus. And at that moment, at that distance, you take the reciprocal of that number, and that's their accommodative amplitude, assuming that you first put their distance correction in place there. Now, in patients who you're measuring accommodative amplitude, they're probably not going to be that good at accommodating in the first place, so you might have to give them a little boost. That is, you don't start with the distance correction. You would start with, say, a +3 add. So how far away would the target be in focus with a +3 add? 1/3 diopters, 33 centimeters. So you'd start this, you'd dial the +3 in, start this at 3 diopters or 33 centimeters away, then you start moving it closer until it goes out of focus. Say it goes out of focus at 4 diopters or at 25 centimeters, then their accommodative amplitude is just 1 diopter. So let's look at some examples of this. Here's a patient who has 4 diopters of hyperopia and an 8 diopter amplitude of accommodation. So in order for this person to see clearly at distance, they have to use up 4 out of their 8 diopters of accommodative amplitude just to see clearly at infinity. So that leaves them 4 diopters left over to apply now to bringing the target in as you move the target in closer. So their near point is going to be 1 divided by 4 diopters, or 25 centimeters away. So their range of accommodation is going to be from infinity up to 25 centimeters away. Now let's look at a second patient who also has an 8 diopter amplitude of accommodation, but now has 4 diopters of myopia to start with. In that case, the far point, the point with accommodation fully relaxed, is going to be, there are 4 diopter myopes, so it's going to be 1/4 diopters, or 25 centimeters away. That gives them a 4 diopter head start, as so to speak, on accommodation. So we take the 4 that's already built into their eye plus 8 that they can apply, and that's 12 diopters total. 1/12 diopters is 0.083 meters, or 8.3 centimeters away. So the range of accommodation of a 4 diopter myope who has an 8 diopter amplitude of accommodation is from 25 centimeters up to 8.3 centimeters away. In both cases, if you give them their proper correction for distance, then they're going to have a near point that's 1/8 diopters away, 12.5 centimeters, because that's their amplitude of accommodation. So now, so how often then do we do this? I mean, you have a patient, they're 42 years old, they're having trouble reading, and are you going to map out their amplitude of accommodation for each eye and figure out where their far point is and their near point with and without correction or through a bifocal or not? You know, are you going to do all that for your average patient? No. All you're really going to do is, you can use a table, or you can just do trial and error in the office, or use your clinical experience to estimate and put something up there, because not every patient needs that kind of a rigorous evaluation. But every now and then you'll have a patient who has asymmetric accommodation, who's prematurely presbyopic, who has some other refractive issue or consideration where you need to know how to be able to do this and assess it in order to help them. Finally, what are the 4 types of hyperopia? This is something I have to review every time I look at it, but they're absolute, manifest, facultative, and latent. And rather than just go through the definitions, let's just go straight to an example. A patient requires +1 diopter to see at distance. I hear flipping around. Does that mean it's not in the notes? So it must mean that it's probably in the notes but lost or misplaced. So it should be there somewhere. So I apologize because I'm hearing the flipping noise. A patient requires +1 diopters to see at distance. The manifest refraction reveals that she'll tolerate up to +2 diopters, and the cycloplegic refraction is +5 diopter sphere. What are the types of hyperopia in this eye? Well, she requires +1 to see at distance, so her absolute hyperopia is 1 diopter. But she'll accept up to 2 diopters, so she has so the manifest hyperopia is +2, and the facultative hyperopia, that is the ability to shift to still be in focus. She has a facility to keep things in focus of 1 diopter, 2 minus 1. Then the cycloplegic or total hyperopia is 5 diopters, and so the latent hyperopia, that only shows up under testing conditions, is 5 minus 2 or 3 diopters. So that's accommodation and hyperopia. And next let's talk about astigmatism. And we'll talk about define a cylindrical lens, the conoid of Sturm and circle of least confusion. We'll look at power crosses and describe types of astigmatism. Look at spherical equivalent and what happens with tight sutures and distortion. So here is your cylindrical lens that's used to correct or cause astigmatism. And that lens, you see, is why it's called a cylindrical lens, is because it looks like a cylinder. So what happens to light as it encounters this cylindrical lens? Well, rather than thinking of light as just a beam of light, I want you to think about light as a whole bunch of vertical planes of light, all one next to each other. And we're going to take one of those vertical planes of light, and what does it encounter as it sees this lens? It's actually easier if I just walk in front of this picture for a minute. So we have a vertical plane of light, and what it's going to see is it's going to see a flat surface. So it's just going to pass on through that lens. It'll slow down, it'll speed up, but it'll just go off. It won't get refracted at all. But if we have a horizontal plane of light, then that horizontal plane of light is going to see a curved surface. It's going to get refracted to a point over here and then go off. And if we take another horizontal plane of light above that, it's going to get refracted to a point as well. And another one below that, it gets refracted to the same point as well. And so if we have an infinite number of horizontal planes of light constituting a beam of light, they get refracted into a focal line. And the focal line is parallel to the axis but perpendicular to the power of the lens. So that is a cylindrical lens. Now, what happens if we want to add a little bit of power to the vertical part of this lens as well? Then we have a spherocylindrical lens, which I show here. Now we have the one focal line from the horizontal power, but now the vertical curvature also gives us a second focal line over here. That distance between those two focal lines, is the vertical and horizontal focal line, is the interval of Sturm. And the geometric figure that's formed by the rays of light as they go from one to the other are called the conoid of Sturm. The circle of least confusion is the circular cross-section of the conoid of Sturm that's halfway in diopters between those two focal lines. So if this focal line is 4 diopters or 25 centimeters away, and this one's 2 diopters or 50 centimeters away, then this one's going to be halfway in diopters, so it's going to be 3 diopters or 33 centimeters away. And why do we call it the circle of least confusion? Well, it's where there's least distortion of the letters as you try to read them. So here we are in the vertical focal plane. You see the horizontal lines are smeared, but the vertical stays okay. Over here, we're on the horizontal image plane, and the vertical lines get smeared out, but the horizontal lines are okay. But in between, yes, there's distortion, but it's equal vertical and horizontal, so the shape of the letter is best preserved, thus the name circle of least confusion. So in an astigmatic eye, you can have then not just a focal point in front or behind the retina, but you have two focal lines now, in this case in front of the retina. And you can correct an astigmatic eye, and you can also have just as you can have a focal point turns into two focal lines, the far point of the eye in an astigmatic eye turns into two far lines. And you can correct the refractive error in the astigmatic eye by choosing a lens whose focal lines coincide with the far lines of the eye. Now the direction of the astigmatic axis is the same in the right and the left eye. It's not symmetric, it's identical. So, and it's every 30 degrees is another clock hour on the astigmatic lens. So how do we then describe a lens that has different powers in two meridians 90 degrees away from each other? You can't just use a single number. You need two numbers and orientation. So one way to do it is with a cross diagram. And in this case, we have a cross with principal meridians labeled with the power acting in these meridians. So we have +1 here acting in the 135 degree meridian and +3 acting in the 45 degree meridian. That's a power cross. Now we can also, though, talk about the axis, because remember I showed how axis is 90 degrees away from power. So the axis cross would be +1 axis 45 and +3 axis 135. These are the identical lens. One's a power cross, one's an axis cross. So, but that can be a little bit cumbersome to try to use these cross diagrams to describe glasses. And we all know that when we have a glasses prescription, that's a sphere and cylinder in there. And we can write it down with some numbers. So how do we get to that at that point? Well, I'm going to go through an example to show you how to do that. So a patient comes into the so you have this cross diagram where you have -1 in the 180 meridian and +2 in the 90 degree meridian, which, by the way, could be the result of a stenopeic slit refraction, which we'll talk about briefly later. Stenopeic slit refraction gives you these two numbers. How do you convert that to a glasses prescription? Well, first, we know that this is a combination of two cylinder lenses, so we can draw it that way. It's +2 on the 90, and it's -1 on the 180 meridian, and this is the combined with symbol. Now let's add across meridians, make sure we did it right. 0 + 2 is 2, -1 + 0 is -1, so that combination is exactly the same. So we can write that out in numbers. This is +2 in the 90 degree meridian, or +2 axis 180, and this is combined with -1 in the 180 meridian, or -1 axis 90. But that still doesn't look right. It doesn't look like a glasses prescription, and that's because it's just a combination of cylinders. We want spherocylindrical notation, a sphere and a cylinder. So to do that, we have to make one of these two crosses into a sphere. Let's make this one into a sphere. So how do we do that? Well, we're going to give it +2 in the horizontal meridian. But what we give to this side, we must take away from this side. So if we give +2 to this side, we have to take away +2 from this side. So -1 minus 2 is -3. So now we have +2 sphere combined with -3 in the 180 meridian, or -1 axis 90. And there's our spherocylindrical notation, +2 minus 3 times 90. Now we could have, instead of making the +2 into the sphere, we could have made the -1 into the sphere. So let's try that. So we put a -1 in the vertical meridian, like so. But what we give to this side, we must take away from this side. So +2 minus -1 is +2 plus 1 is +3. So it's -1 sphere combined with +3 in the 90 degree meridian, or +3 axis 180. And that's plus cylinder form. So that's how you make that transition. Now we also want to know, how do we go backwards the other way? How do you take a glasses prescription and make it into a power cross? So let's look at that. One very straightforward way to do it is to draw two power crosses. So you're given a prescription, +2 - 3 times 90. Draw a power cross to represent that prescription. Okay, you say, we'll take +2 and we'll put it here on a power cross, +2 + 2, give a combined with symbol, and then we have -3 axis 90, which is -3 in the 180 meridian. Now we add across meridians to get it into a single power cross. 0 + 2 is 2. -3 + -2 is -1, and there's our power cross. And we can go back. We can go back to the other, and it's the same as what we just showed over here. Now there's another way to do it that's actually a little faster and requires even less thought if you can remember how to do it. And that is, you write out the prescription in both plus and minus cylinder notation. So you're given this prescription. Let's also write it out in minus cylinder notation, so I'll jump ahead a little bit. How do you convert this to minus cylinder? The new sphere is the old sphere plus the old cylinder. So +2 - 3 is -1. The new sphere is the same as, the new cylinder is the same as the old cylinder, but with opposite sign. And the new axis is 90 degrees away from the old axis. So this is the same prescription written in minus cylinder form and in plus cylinder form. Once you've done that, it turns out it sort of just works out this way, that you can go straight to the power cross. You take the sphere on this one and put it on the axis here, like so. And you take the sphere in this one and you put it on the other axis, like so. I think a student pointed this out to me once in one of the lectures, but it's a quick way to get there without really having to think it through much further than that. And it just works out. And it's not an axis cross, it's direct to the power cross. So that gives us the same result. So as I just said, to transpose from plus to minus cylinder, new sphere is the old sphere plus the old cylinder. New cylinder is the same as the old cylinder with opposite sign. New axis is 90 degrees away from the old axis. Now when you're doing retinoscopy with free lenses, you're doing retinoscopy and you need to turn that into a glasses prescription. You're not just taking it out of the phoropter, and you're using all spherical lenses. So you need to know how to do that. So say you have a patient and you have the intercept horizontal and you sweep it across the pupil. That's going to give you, and let's say that's neutralized with a +2.5 lens. Then you're going to put that you're going to put this as the axis, this is the power, so you're going to put it on the axis cross as a +2.5 that matches up with this axis of the intercept. Then you have to do the vertical. And so let's say in this example, you neutralize with a +4.5 lens. That means the +4.5 is going to go here. And so then to get your final prescription, you write it out. That's plus, you do what we just showed you to convert, to write it out. It turns out that it's +2.5 + 2, axis 90, because it's already an axis cross. But then you do have to subtract your working distance, which if you happen to be working at 2/3 of a meter away, that's going to be 1.5 diopters. So there's your net prescription, +2, +1, +2, axis 90. So you should be able to go from free retinoscopy to writing out the net glasses prescription. Now what happens sometimes, especially in pediatric ophthalmology where we have kids who wear really strong glasses, or if you have a patient who's aphakic, it's ideally you'd like to refract just over those really strong lenses and change and just make little changes rather than put the whole thing into the phoropter, because then you can get errors of addition and vertex distance and all. So we'll sometimes refract over the glasses by putting these Janelli clips on there. They're supposed to be straight up and down. And then now you have a cylinder. So how do you get the new cylinder? Well, one way is there are over-refraction calculators. You see down here you can add the cylinder to this one. But what I do in the office is I then just take the glasses and these clips and the astigmatic lens and put the whole thing in the lens meter. And then you can just read off the whole combination as if it's an unknown glasses power, and that's your net new prescription. Now, sometimes you might be asked to combine cylinders to end up and to figure out sort of generally speaking, maybe not exactly, but the roughly where the combination of those two cylinders end up. And I just want to show you an example of how to do that. So say you have a lens that's +1, +4.5 like so, and then a second lens is +1 and +4.5 like so. If you combine those two together, is the net what's the orientation of the net cylindrical power going to be? Well, to figure that out, first of all, we don't care about the sphere, so we're just going to take all the sphere away. So we'll take away 1 from all 4 of these and just sort of put that aside. So the net question really is you've got a 3.5 this way and a 3.5 this way, and what's the combination of those two? To figure it out, we can break it down into the horizontal and the vertical components. So the 3.5 has some horizontal power going to the left and some going up. This one has some horizontal power going to the right and some going up. So if we combine those two together, then you see the horizontals are going to cancel out, but the verticals are going to add up. And that's our net combination then. So the net answer is going to be there's going to be some amount of cylinder rough at 90 degrees. What are the different types of astigmatism? Remember I mentioned that you have 2 focal lines in an astigmatic eye, and depending on where those focal lines are, that's the type of astigmatism that you're working with. So it can be compound myopic, simple myopic. Compound myopic is if both focal lines are in front. Compound hyperopic is if both are behind. Mixed is if one focal line's in front and one's behind. And then you have rare case of simple myopic or hyperopic where one of the focal lines actually falls on the retina. Now, astigmatism is something that, it's just something about it that patients just, they don't like being told they have astigmatism. So they're told they have a stigma in their eye, and they won't remember the fact that they had a stick in their eye or a needle in their eye, but they'll remember that they've got astigmatism. And it's just one of those things. I actually try to avoid using the terms if I don't want to worry a patient, try to use some other terms, but patients still here, they understand that they have a football in their eye or something. So there are different types of astigmatism. There is with the rule and against the rule. That means with the rule means that the cornea is steeper in the vertical meridian, against is steeper in the horizontal meridian. So why use this kind of odd terminology instead of just saying whether it's vertical or horizontal? Well, part of it is that because we can use either plus cylinder notation or minus cylinder notation, different people use different foreign notations, and so the plus cylinder people have to be able to talk to the minus cylinder people. So if you just say with the rule astigmatism, then everybody knows that that means that the cornea is steeper this way. Tends to be true more in younger patients that you have with the rule astigmatism. Probably because their corneas are more pliable, plus their eyelids are more elastic, so that's going to push on the tops and bottoms and cause the middle to bow out. Older patients tend to develop against the rule astigmatism. If the axis of correcting cylinder is not within 20 degrees of the vertical or horizontal, then it's oblique astigmatism instead of plus or minus. And then it can be symmetrical or asymmetrical, depending on the orientation of oblique astigmatism. So, for those of you who are trying to build your refractive surgery practice, you can say, you can present your patient with the results of your refraction and say, well, Mrs. Jones, I'm afraid I have some terrible news. You see, I've discovered that you have astigmatism in your eye. You have astigmatism. Not only do you have astigmatism, but you have compound myopic astigmatism against the rule. But we can fix it with a laser. And thus you'll... that's the thing is that I actually envisioned that when I was a kid that maybe someday I'd grow up to be a stand-up comedian or something. But here it's better because I can tell my jokes, but if nobody laughs, I still get paid. How do you tell if a patient has compound myopic astigmatism or simple astigmatism or whatever? Well, you simply write the prescription in both plus and minus cylinder form and then look at the spherical power, because those are the two numbers that are going to go on the arms of the power cross. And if both arms are positive, it's compound hyperopic. If both arms are negative, it's compound myopic, etc. So we can look at a couple of examples. Here's a patient. We write out the prescription. Here it is in plus cylinder notation. We write it out in minus cylinder notation. You see this one's going to be plus and a minus on the power cross, so that's mixed astigmatism. This is going to be a plus and a plano on the power cross. That's simple hyperopic. Those are both plus, so that's compound hyperopic. So spherical equivalent is just the average power of a spherocylindrical lens, and it's equal to sphere plus half the cylinder. That number, the spherical equivalent, is what places the circle of least confusion on the retina. So let's look at an example. What's the spherical equivalent of minus 1 plus 2 times 45? Well, it's the sphere, which is minus 1, plus half of the cylinder, plus 2. And the combination is plus 2 divided by 2 is plus 1. So negative 1 plus 1 is 0. So the spherical equivalent of this lens is plano. And in fact, that's the prescription for a 1 diopter Jackson cross cylinder, with the axis depending on how you hold the Jackson cross cylinder. And we'll talk about Jackson cross cylinders a little bit more later. But they have plano spherical equivalent, which is key. Now here's one that comes up and that I like you to know about, because I think that it can have clinical implications. A patient has keratometry of 40 in the 30-degree meridian, 46 in the 120-degree meridian. What is sort of astigmatic correction would you expect to see? Again, I hear a little bit of flipping of pages, but I'm pretty sure it's in the notes. If not there, then it might have got lost. So the answer to figure this out is that you see there's 6 diopters between the two meridians, 6 diopters of cylinder. So and furthermore, the 120-degree meridian is the steepest. So to fix that, you would want to put minus 6 diopters. One way to fix it would be put minus 6 in the 120 meridian. So therefore, minus 6 in the 120-degree meridian would be minus 6 axis 30. Therefore, one way to correct this, the astigmatic part of this refractive error would be minus 6 axis 30. So if you look at the glasses prescription and you're not seeing minus 6 axis 30, roughly, it's not exact because it depends on the vertex distance, for example. But if you don't see about minus 6 axis 30, then that means that it's not all corneal astigmatism. It means that there's some lenticular astigmatism in there as well. And so if you're planning refractive surgery on a patient and the corneal astigmatism isn't corresponding to the refractive error, then you could end up in trouble if you take away all that corneal astigmatism. There's a way that disregards the spherical part of the correction, but the focus here is on the cylindrical part. So if you have a patient who has tight sutures, how exactly does that lead to astigmatism? And that always was a mystery to me for many years, until I taught this course for a few years and finally figured it out. Here's a patient who's had corneal surgery and the sutures tie just the right tension, and so there's no distortion of the cornea at all. Now, in my view, it seemed to me that if you tie that suture too tight, it's going to make the cornea flatter, but everyone told me, no, the tight suture makes it steeper in that meridian, and the attending would say, no, cut the high K, cut the suture where the K is the highest. And so I finally figured out that, yeah, that I was kind of right, but so was everyone else. So a tight suture does flatten the cornea, but it flattens the cornea where the suture is, and then you get a compensatory steepening of the rest of the cornea. And the compensatory steepening happens over the pupil, and that's the only part that matters for refraction, is what's going on over the pupil. So that's why you end up with a steep cornea from a tight suture. You cut the suture, that allows this to flatten, to steepen, and you get a compensatory flattening in the center. There are other aberrations in the eye that I want to mention, important aberrations, 2 in particular: spherical aberration and astigmatism of oblique incidence. Spherical aberrations where the peripheral rays are refracted more strongly than paraxial rays. So that in this example I have here, with a biconvex lens, the central rays, they don't see as much curvature. The peripheral rays see more curvature, so they get refracted more strongly. So now you end up with these aberrations that cause distortion and reduce the best visual acuity. Where is that clinically important? Well, we see it when we're doing retinoscopy, especially in young kids whose pupils dilate widely. I don't know if you've seen this before, but you'll see with movement centrally, but you'll see against movement peripherally, and then you don't really know, well, which part of the refraction am I trying to neutralize here? The reason that that happens is that because of spherical aberration, where there's just the lens is stronger in the periphery than it is in the center. The practical outcome is that you want to concentrate your refraction on the center of the pupil, because that's the part that's still going to be exposed once dilation wears off. There are ways to make lenses that reduce the spherical aberration. For example, spectacle lenses have this sort of meniscus shape that reduces it, or your indirect ophthalmoscope lens has what's called an aspheric lens surface. But those lenses are designed to be used only one way. So if you've ever, you have this white ring and you're not supposed to have the white ring showing when you're examining the patient, and that's because of spherical aberration. You see the severe spherical aberration when the lens is held upside down. You get much more magnification out here in the periphery, whereas it's nice and flat all the way across when you use the lens in its proper manner. Astigmatism of oblique incidence is what you get when you tilt a lens. So tilting a spherical lens induces astigmatism. Tilting a plus lens gives you plus cylinder with the axis and the axis of tilt. And tilting a minus lens gives you minus cylinder with the axis in the axis of tilt. You also get a little bit of sphere to the same degree. So you may have, I don't know if you've ever noticed, you sort of look in the back of an audience and you might see a patient, probably nearsighted, and they've kind of got their glasses sort of tipped up like this. Are they trying to get more astigmatism correction? No, but they're getting that little bit more of sphere as well. They're probably under minus, so their glasses need to be a little stronger. You can sort of diagnose that they're under minus because they're tilting their glasses up like on the beach. So there's two things to get more minus power. There's the person on the beach and they're pushing their glasses up like so. But then if they want to get even more minus power, you would go like this. But that looks goofy, so nobody's going to do this on the beach. Where else do you see that a small amount of sphere, the same sign is induced? Undercorrected myopes tilt their glasses, gaining cylinder and sphere. The other clinical take-home of that is that if you try to do retinoscopy from the side, you'll get against the rule of astigmatism. And you can work this out if you sit down and think about it. But the lens, there's a 60 diopters of plus power in the eye. And if you get oblique to that, then you're going to get plus cylinder induced in the axis of tilt. And so then you're going to have to correct that with plus cylinder opposite of the axis of tilt, which is going to have the with axis opposite the axis of tilt. Let's next talk about the differential diagnosis of various refractive errors as a way to sort of bring together some of these thoughts about effective lens power, axial length, and how it contributes to refractive error. And this is one of the ways, too, that a clinical scenario can be used to sort of probe your understanding of optics. So a patient comes into the office who has an increase in their myopic correction, progressive increase in their myopia. And why might that be? Well, one cause of progressive myopia could be what's shown here is keratoconus. Keratoconus, the cornea becomes steeper, the eye becomes stronger, the eye becomes more myopic. Notice this cornea is steep enough that you can almost sort of see the angle structures. Another cause, here's a baby with big, beautiful eyes, but maybe they're too big and maybe they're too beautiful. In fact, this patient has 20 diopters of myopia because the eyes are enlarged from glaucoma. And there are patients who have, I've seen malpractice cases where kids come in for tear duct, they get recurrent tear duct probings, but no one ever does a refraction. No one ever looks at the optic disc, and it turns out that they're congenital glaucoma patients and they're tearing for that reason. So myopia, progressive myopia from increased axial length can also be a factor. And I use this in my aphakic children because I can't always check their pressure. And so, but if I see a myopic shift, then that might push me over the edge to get an exam under anesthesia. So this congenital glaucoma was missed. This one would be harder to miss. Differential diagnosis of acquired myopia then. Things that make the eye too strong, increased refractive power of the eye, and that would include keratoconus. Lens changes such as cataract, lens dislocation anteriorly. Cataract can cause increased myopia both from changing the shape of the lens, but also by changing the refractive index of the lens, because a cataractus lens has a higher refractive index. Diabetic changes as well. The lens can swell and become more round or get a higher refractive index. Or excessive accommodation, accommodative spasm, inadequate fogging by the examiner. So things that make the eye too strong, or things that make the eye, drugs, miotics, Topamax, anything that pushes the lens iris diaphragm forward is going to make the lens stronger inside the eye and cause a myopic shift. Or things that make the eye too long, and that could include a posterior staphyloma, congenital glaucoma, a scleral buckle. Pull that scleral buckle on nice and tight, make the eye 1 millimeter longer or 2 millimeters longer. That's going to be 6 diopters of myopia. Here's something that makes a patient that comes into your office and they've had a hyperopic shift. And you say, well, that's odd. You know, I don't usually see patients become more hyperopic. And you think, I wonder what could cause that. And you had sort of passed on the retinal exam the first time, but then you say, you know, maybe I better just double check. And you look again and you see there's choroidal folds. And the choroidal folds are because there's something pushing the eye forward and making the eye shorter. There's a tumor behind the eye. So here you've used your knowledge of optics to maybe save the patient's life by diagnosing a tumor in the orbit. Another thing that can make the eye shorter would be central serous retinopathy, which doesn't make the eye shorter, but it pushes the retina forward under this layer of clear subretinal fluid. One of the hallmark features of central serous retinopathy is a hyperopic shift. So things that can cause acquired hyperopia would be things that make the eye too weak, decreased refractive power of the eye, lens changes, anything that would dislocate the lens posteriorly within the eye, or aphakia, of course. Poor accommodation through drugs, 80s tonic pupil trauma to the eye, definitely seen that regularly. Chloroquine, or any drug that can interfere with accommodative ability, can also reduce the refractive power of the eye and cause what appears to be acquired hyperopia. Or things that make the eye shorter, including a tumor, choroidal or orbital tumor, or decreased effective axial length with central serous retinopathy. And then there's the matter of acquired astigmatism. A patient comes into your office and they have more astigmatism than they had on the last visit. What could cause that? Well, here there's a pterygium that's sort of pushing on the cornea to the side and causing it to warp centrally. Here's a patient with Terrien's degeneration that's causing the corneal changes over the pupil as well and more astigmatism. Here's a patient with posterior lenticonus that causes both myopic change but can also cause astigmatism. So what can cause astigmatism in the eye, a progressive in particular? It can be corneal causes or lenticular causes. Corneal causes would include just simple astigmatism. Anything pushing on the eye, didn't show a picture, but we've seen, we use this as a decision whether to operate on a child with a hemangioma of the eyelid. If it's pushing on the cornea enough to cause astigmatism, then we'll be more aggressive with it. A chalazion can do it too, a tumor, even just congenital ptosis, you can get more astigmatism as a result. Structural abnormalities, keratoconus, like I showed earlier, that not only makes the eye too strong, but also adds an astigmatic error. Terians or pellucid marginal degeneration, or lenticular astigmatism. So lens causes would include simple lenticular astigmatism, lenticonus, as I showed, lens dislocation off to the side instead of to and fro. A lens coloboma could cause it, or a ciliary tumor. The first sign of a ciliary tumor could be a change in the stigmatism as a result of the tumor pushing on the eye. I just saw a patient the other day, and he has pretty severe form of Marfan's, but he has hardly any zonules, and so instead of his lens being dislocated to the side, where Marfan's is pretty typical to see side lens dislocation, this patient's lens is just unsteady in the eye, and some days his chamber is kind of shallow, and other days his chamber is deep. When it's deep, you see iridodonesis. When it's shallow, he gets like 5 more diopters of myopia, but the iris doesn't wiggle. So he's going to get the lenses taken out, but right now he's in that state. That's a ciliary tumor that can push on the lens and cause acquired astigmatism. So that's differential diagnosis for refractive error. Now we want to talk about correcting refractive error through contact lenses, refractive surgery, and intraocular lenses. Let's talk about contact lenses first. They'll talk about the clinical evaluation, power calculation, evaluating the fit, and then again I'll come back to comparing keratometry with refraction because it matters. So when we're fitting a patient for contact lenses, we want to look at the corneal contour, we want to assess the tear film, look for eyelid abnormalities, look in advance to see if they have any signs already of papillary conjunctivitis, and look for eccentric pupil. But mostly what I want to focus on is the refraction and the fitting. For the refraction, you could just put on a trial lens and then refract over that, and that's probably the way it's mostly done. Or you could calculate the whole thing. You do need to perform a vertex distance correction, and you should compare the keratometry with your refraction to look for lenticular astigmatism. So say you have a patient coming into the office who wants hard contact lenses, and you don't have any trial lenses available. Is there a way to calculate the lens power that you might, and shape, curve that you might use to correct that patient's refractive error? Yes, it can be done, and you do it. There's a few steps to it. You need the refraction and the keratometry readings, and then you're going to choose a lens whose base curve is steeper than the flatter K, a half diopter steeper. Now, what does that mean? We want to choose a contact lens that's going to match the curvature of the cornea. And so if you think about trying to match a curve that's, if the whole cornea is spherical, that's easy. You have just one number. But if part of the cornea is steeper than the other, say it's steeper in front and behind and flatter to the side, then you're going to want to actually match the flatter side. So imagine that I'm standing on a mountaintop, and the mountaintop is sort of flatter side to side, but it's steeper front and back. Well, and I want to choose something that's relatively stable to stand on. I'm going to choose a curve that matches the flatter surface, and then the steeper is going to drop off in front and behind. That seems to work best. Then what happens in the eye is that there's not somebody standing there, but what happens is the tears come in then and fill the gap on the steeper side. So the take-home message of that is we choose a base curve that's steeper than the lower K, but you can't have it exactly matching because then there's no room for tears, so you want to vault it by a half diopter over the surface of the cornea. So you choose a lens that's 0.5 diopters steeper than the flat K. Then you convert the refraction to minus cylinder form and to 0 vertex distance. And we can disregard the minus cylinder because those tears that fill in under that fill in those spaces where it's steep, those are like a minus cylinder lens. And then we finally have to subtract the tear lens from what's ground into the front of the surface because that little vaulting actually adds a little plus power behind the lens. So let's look at an example. Patient comes into your office with a refraction of plus 11.5 plus 1 times 35 at 13 millimeter vertex distance with keratometry of 44.25 and 45.87. What contact lens do you estimate, hard contact lens, could correct the refractive error? Well, the first step is we want to choose a hard lens whose base curve is just above the lower k. So the flat k is 44.25. We add 0.5 to that to vault over the cornea. And so our base curve is going to be 44.75 diopters, which you could convert to a radius of curvature if you have a converter. Just a reciprocal, basically. Then you convert the refraction to minus cylinder form. So here's the plus cylinder form. New sphere is the old sphere plus the old cylinder, so 11.5 plus 1 is 12.5. New cylinder, same as the old cylinder, but with minus power. New axis, 90 degrees away from the old axis. Now we disregard the minus cylinder. Just throw that away, and so 12.5. So is 12.5 the power that we're going to need? No, because that's at 13 millimeter vertex distance. We need to convert to 0 vertex distance, so we take a reciprocal at 12.5. That gives us a number. We subtract 13 from that. We take the reciprocal of the new number. The reciprocal of the new number is 15. So is that the power that you grind into the front of the contact lens? Not quite, because remember we vaulted a half diopter over the cornea, so we've got to take a half diopter off of what's ground into the front of the lens, but it'll be a 14.5 diopter, 44.75 base curve lens. Then how do you look at it and evaluate the fit? Well, the basic thing you want to look for is that you want to see that you can put fluorescein in the eye with hard lenses, and you want to see that the tears are filling in that little bit of gap. Here, the lens is too flat, and so you can see apical touch with pooling above. That's going to be an uncomfortable lens because the eye is starving for oxygen right there. This is an eye with astigmatism, and this is what I was saying to you before. Here's the flat meridian, the lens fits that way. Here's the steep meridian, and the tears go in to fill up that space. I really like that picture because it shows that astigmatic lens filling it. Kind of makes sense. You replace the warped cornea with a clear cornea, the astigmatism will go away. That's how you assess fit with a hard lens. What about a soft lens? You can't put fluorescein in the eye with a soft lens or it ends up staining the lens. In that case, you evaluate the movement of the lens with a blink. If the lens moves too much with a blink, then it's too flat. If it doesn't move enough, it's too steep. It's the difference between having just a piece of saran wrap in the eye. You can imagine that's going to move around a lot when the patient blinks because it's too flat. Whereas if you have a little suction cup on the eye, it's going to stick and it's not going to move at all when the patient blinks. So how do we steepen the lens? We can either increase the diameter or decrease the radius of curvature. And let me show you what I mean. So here's a lens with a constant radius of curvature. If we choose two different diameters, one's going to have fit more steeply than the other. Here's a bigger diameter, and you see the curvature that's shown. Here is a shorter diameter, a smaller diameter, and you see the curvature shown. If you look at the contour, you see the larger diameter just looks more curved. That's more likely to suction cup onto the eye than this smaller diameter. If you had an infinitely small piece, it would just be flat, completely flat. So that's one way. Increase the diameter, steeper lens. The second way to do it, given the same radius of curvature, given the same diameter, would be to change the radius of curvature. And you see a shorter radius of curvature in green makes for a steeper lens. So keeping the diameter the same now, that's the shorter radius of curvature. That's the longer radius of curvature. So a patient comes into your office and they wish to be fitted with soft contact lenses. You fit them with the contact lens. They come back a week later, they say, well, my vision's fine, but the lens is uncomfortable. What do you do, doctor? Well, you say, I take a reciprocal. No, wrong. You say, well, I would sit the patient in a slit lamp and have them blink to evaluate the fit. Oh, okay, well, you sit the patient in the slit lamp, you have them blink, and you see that the lens moves excessively. Ah, the lens moves excessively. That means it's too flat. It needs to be made, we need a tighter fit. Well, how do you gain a tighter fit? Well, I would either increase the diameter of the lens or I would decrease the radius of curvature of the lens. If the lens has if a contact lens, hard lens is very high minus, then the edges can get caught under the upper lid, but they can be beveled down so they don't get stuck that way. And if lenses are very, very hyperopic, then the edges are too thin and they can drop too low, but you can have them give a little flange there that's called a minus carrier. That's kind of advanced stuff, but just mention it. So then the patient doesn't want contact lenses. They want refractive surgery. So obviously it's beyond the scope to go too far into refractive surgery. I just want to describe some of the optical principles behind refractive surgery. So the basic idea here is what are we doing to the cornea to change its refractive power? Well, one thing to consider before we even get into that is to recognize that the cornea has spherical aberration, which means that, but some of that spherical aberration is actually complementary to what's in the lens, and so you end up, they can actually work together to reduce the aberrations in the eye as a whole. When you change the aberrations of the cornea, you can actually increase spherical aberration of the eye as a whole. The other thing to consider, as we mentioned earlier, is the cornea has a front and a back surface. And so sometimes if you change something to the front of the cornea but destabilize it, you may also change the curvature on the back surface, and if you don't take that into account, you can end up with surprises. So what are we doing what was done when radial keratotomy was performed? Well, in that case, the eye's too strong, so these cuts were made in the peripheral cornea, which caused the periphery to actually get steeper. It destabilized the periphery and flattened the center of the cornea to reduce the power. Astigmatic keratotomy, you cut the periphery here to again destabilize the periphery and flatten the center in this meridian. More often now, of course, we're doing procedures to sculpt the cornea to its desired shape. So the basic idea in LASIK, or PRK for that matter, is that we're basically flattening the front surface of the cornea, increasing its radius of curvature, reducing its power, and reducing the correction. In hyperopic refractive surgery, something's being done to sculpt the periphery to make the center steeper. So that's a little harder to do because you have to take away tissue from the periphery to make the center steeper. Another way to achieve that, to make the center steeper, is conductive keratoplasty, where the periphery of the cornea is burned and you get this constricture, this tightening of a band around the periphery of the cornea, and then you get a compensatory steepening in the center. For astigmatic refractive error, you have to reduce the amount of, you have to ablate different amounts in one meridian than in another. And in order to do that, one way to achieve that, among others, is to use a mask over the eye so that you're ablating part of the mask before you get to cornea in one meridian, but not the other. So what happens when you do refractive surgery? Why do you get these optical aberrations that cause problems, and what are they? Well, we go all the way back to the beginning of the lecture from this morning, or was it yesterday? You can get diffraction of light, which is when the light passes through the apertures or across or adjacent to that radial keratotomy scar. And that diffraction can cause like a starburst sort of a pattern. You get scatter of light, and that can be caused by a hazy flap surface. That irregular ablation, you get the irregularity, so light's going to scatter. You can get multifocal corneas. So like a fly's eye, you get different optical zones within the pupil, and that's going to give you different separate images that can cause patients some great distress. Larger optical zones make it less likely that you're going to have a multifocal cornea at the end. It used to be a bigger problem. You can get coma if you have an off-center treatment. Coma is like a comet. The light flares off to one side more than the other. And you can get spherical aberration. And remember, I said the eye already has some spherical aberration, but the spherical aberration of the cornea somewhat works against the spherical aberration of the lens so that the two kind of add up. And so if you take that away, then you can get more. And that can cause halos around objects. So a lot of that can be reduced by doing customized ablation that looked at the whole optics of the pathway all through the eye on a double pass through the eye, wavefront optics. And then you can break down all the aberrations of cornea and lens into spherical, cylindrical, and irregular components and treat in that way to try to make super eyes that have no aberrations. So finally, in this section, I want to talk about intraocular lenses and the power calculations that go with. And you're hanging in there, so we're going to, then we'll take a break after intraocular lenses. So there are theoretical formulas and there are empirical formulas to IOL calculations. The theoretical formulas are derived from optical principles, and in those formulas, the effective lens position is critical. You know, I keep hammering on that, effective lens position. Where that lens is in the eye is key. The older formulas were not very good at it. The newer formulas are better at it. But because the older formulas were not great at figuring out where the lens ended up, we ended up relying on the empirical formulas. Those don't rely on the schematic eye. It's just Saunders, Retzlaff, and Kraft, SRK. They did a whole bunch of cataract surgeries. They measured the axial length, the keratometry, and the lens power that went in, and the outcome, and they plotted it and put it in a computer and calculated a straight line regression curve, and out came their SRK formula of A minus 2.5 times the axial length minus 0.9 times the keratometry gives the power needed for emmetropia. The A constant depends on the lens that you're using. It actually depends on the lens position, the effective lens position. And then this is the axial length and the keratometry. So this is a simple formula. You can do it by hand, and 90+% of the time it's accurate. You do run into problems, though, if you get short eyes or long eyes, because it's no longer linear. There's a linear range, but short and long eyes, you begin to get errors, and especially in short eyes. So SRK was modified to the SRK2. Still simple enough. You just add 1 for axial length 21 to 22, 2 if it's 20 to 21, 3 if it's less than 20. So the shorter the eye, the more you add to the A constant. Long eye, you take a little bit away from the A constant. And that gives you even more accuracy, maybe 95, 93% of the eyes, something like that, 95%. So for the most part, that SRK2 is all you need. But for very long and very short eyes, you really need to move then to the theoretical formulas, which have gotten much better now that they're better at predicting the effective lens position within the eye. And that includes the SRK-T, T for theoretical, the Holiday, the Hoffer-Q, there's others out there. You have to use a computer to get the numbers, but most of the A-scan units now have those built in. So you'll get something out that's one of the theoretical formulas. And you especially want to look at those if there's a discrepancy, if you have a short eye or a long eye. I'm a surgeon, you say. I don't care about optics, and I don't want to study IOL calculations. So sue me. So yes, you can get sued for doing a bad job on your intraocular lens calculations. In the suits that I've been aware of, one of the key problems was that there was a failure to measure axial length in both eyes. Because if you have a patient who has the same refraction and the same keratometry measurements, but yet the axial length is 2 millimeters different in one eye than the other, well, then you should see 6 diopters of difference in refractive error. And if you don't, then maybe there was an error in your axial measurements. Now, maybe not. Maybe the lens is hard or something, something else. But at least it should be checked and looked at and considered. And when I used to help residents in cataract surgery, every now and then I'd stop the case because things weren't adding up, and we'd redo the axial length measurements before we'd start the surgery. The other place that I've seen that I've heard of is when the patient didn't have the contact lenses removed before the keratometry was done. because that can flatten or change the corneal power by about a diopter. And the recommendations vary on this. Some say at least 2 hours, some say 2 weeks. For refractive surgery, it's more like a month. But you know, it's only a diopter. Probably it led to a suit because, you know, the patient ended up off by just enough that they had to have a lens exchange, and then they had a complication from that, something like that. The most egregious case that I've seen, it wasn't a case actually, but it was just a case I heard about, was a new technician measured the keratometry with the contact lenses still in the eye. So that gave a big error and led to an IOL exchange, but not a lawsuit. So it's diopter for diopter when the error is in keratometry, but a millimeter of error in axial length gives a 2.5 diopter error in the refraction. So axial length has to be measured carefully. And again, SRK alone isn't going to do it if the eye is less than 22 or more than 24.5 millimeters long. So what we've covered then in this second section is visual acuity testing, refractive error, accommodation, astigmatism, and then correcting it with contact lenses, refractive surgery, and intraocular lenses. So I think this is a good time to take a break. In our next section, we'll be talking about other optics of note. So we've made it to part 3. As you'll see, we're getting more, we're trying to get more clinically, directly clinically relevant as the day moves forward, now that the basics are behind us. The next break we'll take will be for lunch, and you know, for those of you watching at home, I'll want you to also eat lunch at the same time. We're going to bring box lunches in to save time, to try to keep the amount of time down. And you know, some of you might think, well, gee, maybe it'd be better if we like stretched this out over the course of a week and had a couple hours and thought about other stuff, and you know, didn't have this like intense, even a short lunch break just to get it that much shorter. But I go by the advice my brother gave me when I was little. He said, David, if you have to eat a turd, don't nibble on it. So, so with that, let's continue into the into other optics of note. So we're going to specifically talk about magnification and telescopes and tie that into low vision and mirrors and then prisms as well. So magnification and telescopes. First, we'll talk about the types of magnification, simple magnifier, telescopes, and then the magnification effects of refractive correction and anisoconia that can result. So in magnification, there are 3 types we want to talk about. Transverse, which is a change in the height of the image. Axial, which is a magnification in depth along the axis. And then angular magnification, which is when we are viewing something with an eye or using a telescope or loops. But transverse magnification brings us all the way back to our U plus D equals V, sort of the diagram that we were doing yesterday, or whenever that was, last week. So, no, it was this morning, that's right. So we're getting it all done today. So it's just, so here's that picture I showed you where we have image and object and the central ray, and the magnification is the image height divided by the object height. But that we don't always know, but what we always know from these calculations is image distance divided by object distance, and that's the same. That also gives us the magnification. So magnification is image distance over object distance. So in books, you'll tend to see it as like a cursive U and a cursive V for the reciprocal of U and V. But I find that I start to get my reciprocals and cursives mixed up. So if you just say image distance over object distance and work it out that way, it's, I think, your safest bet. In the eye, too, we can look at transverse magnification. Again, remembering the 17 millimeters. Should be a... Sorry, let me just edit this lecture. You know, you've heard of procrastinating. and I'm actually working on my lecture while I'm giving it. Oh, that's still wrong, 15.5. We'll fix that again. Okay, there we go. So the 17 millimeters and then the central ray passing through the nodal point so we can figure out magnification of the eye. The problem is when you're starting to look at magnification of the eye, people have different axial lengths, and so it's not always going to be 17 millimeters. So this only applies in certain generalized cases. Axial magnification is magnification along the axis, and it turns out that it's the square of the transverse magnification between any two given conjugate points. So this is going to cause distortion in 3D images, because if here's the object, if the image height now is twice the object height, well, the image depth is going to be 4 times that, the square of 2. And so you're going to get this distortion of depth. And we'll get back, we'll talk about that more later. Angular magnification is when we're looking at objects or images at infinity, because there, if image distance is infinity, image height is undefined, and so you can't do that ratio. It doesn't work. So when viewing with an eye, we have to find a different way. So that what we use is angular magnification. So if I'm looking at the moon, and say the moon takes up 1 degree of my visual field, and now I look at the moon through binoculars, and it now takes up, say, 3 degrees of my visual field, then that means those are 3x binoculars, because the angular amount of the angle of my visual field it's taking up has gone up by 3. So that's the basics of angular magnification. Now, when we're looking at something at the moon, that's simple. When we're looking at something up close, it can get a little bit more complicated with a hand magnifier. Because if I'm looking at say an ant that's walking around on the desktop here, it's going to look a certain size. If I now put a magnifying glass up there, it might look 3 times bigger than it was without the magnifying glass. But I can also make the ant look take up 3 times more of my visual field just by moving closer or further away. So the comparison doesn't apply, because when you have the magnifying glass up there and it's parallel rays of light coming out, as you move closer and further, it doesn't change the angle as much. So what you need is a standard, basically. And so the standard for a hand magnifier is we say that it's the angle, the difference in the angle that it takes up, compared with when there's no magnifier at a set reference distance of 25 centimeters. So if we use 25 centimeters then as our reference distance, as is shown here, and we want to know the difference between that and this, then we can do the math, and it's theta tangent -1, blah, 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 d over 4. So the power of a hand magnifier is d over 4. So, for example, if you're using a 20 diopter lens as a hand magnifier to look at the ant, it's 20 over 4 is 5x. So the ant is going to look 5 times bigger through my magnifier than it would look if I took the lens away and positioned myself 25 centimeters from the object. Note that you could also describe that as d times 0.25 meters. That is d times the reference distance. And so if someone wants to change the reference distance to, say, 40 centimeters, it would just be d times 0.4 instead of d times 0.25. When we look at the eye through a direct ophthalmoscope, you may not realize this, but if you're emmetropic and the patient's emmetropic, there's no lens in there. All it is, it's a light source for you to look into the eye using the optics of the eye as a hand magnifier. The 60 diopter power of the front of the eye is essentially a hand magnifier. The power is then 60 diopters. D over 4 is 15x. So when you look at the optic disc through your direct ophthalmoscope, it's 15 times bigger than it would look compared with if you ripped the optic nerve out of the back of the eye and held it exactly 25 centimeters away. Now for telescopes, we're looking at things off in a distance, and so now it becomes less important at the distance, because if you're standing on your tiptoes or squatting on the ground, it's still basically infinite distance away, so you no longer need a reference distance. What instead you have is you have parallel rays coming into a telescope, and you need to then have parallel rays coming out. And in between those two lenses in an intermediate image plane. So basically, the light comes in parallel. Here's the lens. It now causes the rays to converge. And then they reach an image plane, then they diverge again. Then a second lens changes them back to parallel rays of light. And this difference in focal lengths is like a lever that adds to the magnification of the image. And so the magnification is just the ratio of the focal lengths, which, if you take reciprocals of each, is the power of the eyepiece divided by the power of the objective, is the power of this astronomical telescope. The length of the telescope is the sum of the two focal lengths. Now, Galileo had a better idea. Now, the problem with the astronomical telescope is, you see, if you follow this ray, it goes from top to bottom, and this ray goes from bottom to top, and so the image is inverted. So Galileo had a better idea. Galileo said, oh, I know. I don't know if he said it that way. He said, if we take the same objective lens, but now before the rays of light have converged to form an image, we put a minus lens in the path and diverge it out. So we still have parallel rays of light coming out, parallel rays going in, and we still have these two focal lengths. We still have our lever effect, but now the telescope's going to be shorter because it's this, because the focal lengths overlap, and the image is going to be upright. So the magnification of a Galilean telescope is still power of the eyepiece over power of the objective. Same as with an astronomical, but it's an upright image, and the telescope is shorter. So most of you buy surgical loops will buy these Galilean telescope loops that then just have an extra add on the front, so that so if you want to use it at a 33 centimeter working distance, you just put a +3 add on top of this Galilean telescope. So to summarize, if we have a +20 diopter lens used as a simple magnifier, it's going to be D over 4, or D times 0.25. It's going to be 5x angular magnification. If we use a -20 +4 telescope, it's 20 over 4 is 5x when the -20 lens is the eyepiece and the +4 is the objective. If you were to turn those around, if you were to turn the telescope around backwards, it would be 1/5 x minification. And a +20 +5 telescope is going to be 20 over 5, or 4x. The +20 +5 telescope, though, is going to be longer because the focal lengths overlap. The -20 +4 telescope is going to be shorter because the focal lengths overlap. The longer one, they don't overlap, they add. The +20 +5 is going to be an inverted image. The -20 +4 is going to be upright. Why do patients say that things look smaller when they're over-minused during a refraction? Well, what happens is you put too much minus in the trial frame. That's like the eyepiece of a Galilean telescope. Then the patient dials in plus power into their eye. They're accommodating. That's like putting more plus power all the way inside their eye. So they're viewing the world through a backwards Galilean telescope so that things appear to look smaller. And in general, when we talk about magnification in the eye, we have to do a little bit of a mental exercise here to understand what it means to be aphakic in a different way than is maybe intuitive. And that is, if we were to take someone with emetropia, no refractive error, and inserted a minus lens inside their eye, how would you correct that refractive error? You'd correct it with a plus lens. So we call it an error lens. So we're putting a minus lens inside of a normal eye to simulate refractive error. So that's inside of the eye with its lens still intact. Now we've got to correct that with a plus lens up front here. And what you see, what we have then is the minus lens is the error lens, the plus lens correct. Now this aphakic patient is viewing the world through a Galilean telescope. What's the magnification? Power of the eyepiece over power of the eyepiece, over power of the objective, 12.5 over 10, or 1.25x. So 1.00x is no enlargement, so 1.25x is 25% enlargement. So an aphakic patient wearing spectacle lenses is going to have 25% enlargement of the image. If we instead correct that with an intraocular lens, like so, now here the aphakic lens is a plus 10, but the intraocular lens is going to be a plus 11.75 in this case. Now the Galilean telescope is 12.5 over 11.75, which is 1.06x, or only 6% enlarged. So a contact lens gives less magnification than a spectacle lens for the same refractive error. And an intraocular lens would be even less magnification. Even correcting refractive error with ordinary spectacle lenses does cause some magnification, and you kind of have an intuitive sense of that. If somebody's wearing plus lenses, their eyes look big. If they're wearing minus lenses, their eyes look smaller. And the number is 2% per diopter of power at the standard vertex distance. So you can calculate that then, because it can be a clinical problem of anisoconia. Anisoconia is when there's an image size difference between the eyes. We can tolerate 6 to 7% of different, usually, and a typical adult can tolerate that. Children can adapt to much larger degrees, so I have patients who have 10, minus 10 or 12 in one eye and plano in the other. I just give them the whole thing, and eventually they learn to adapt. So here's an example of anisoconia, and this may become a clinical problem, for example, after cataract surgery if you have a refractive surprise. So if the right lens is minus 3 diopters and the left lens is plus 1 diopter, then the right lens is going to be 2% smaller, is going to be 3 times 2 equals 6% smaller, whereas the left lens is going to be 1 times 2 is 2% larger, so the difference between eyes is going to be 8% difference. And that's probably going to be too much for the patient to be able to tolerate. They may complain of double image or inability to fuse or something of that nature. So how would you fix that? Well, of course, you could give the patient a contact lens, because then the difference in magnification is less. If you wanted to completely obliterate any difference in image size, you would actually give the patient a, for example, you could give the patient a minus 4 contact lens, because then both spectacle lenses would be plus 1. And then there'd be no magnification difference between eyes. So for magnification, we go to low vision, and we'll talk about the approach to the patient, Kestenbaum's rule, near aids and distance aids, emphasizing the near aids, and non-optical approaches to correcting low vision. So in low vision, generally the patient is going to have a lot of different needs, but you can't address all of them in one sitting, so you have to do it in little bits. The most typical thing that patients want is they want to be able to read better. So that's generally the first emphasis on a first visit with a low vision patient. Of course, the thing you need to know up front is what's their visual acuity, and they can't see that well, so you need to do, you can either, to get their best refraction in place. A lot of these patients have kind of been given up on by their doctors, and so the refraction isn't even right once they couldn't help get them back to normal function. We want to know their visual acuity, so you can either use these low vision cards or simply move the patient closer to the eye chart as we discussed. And then you have to be aware of the kinds of devices that are available to help patients. So what I want to talk about is plus lenses, loupes, electronics displays, and non-optical aids for low vision. So, but when we think about the patient who wants to read, though, one place to start is with Kestenbaum's rule. And it's used to estimate the strength of a plus lens that would be required to read newspaper print without accommodation. So to determine this, you measure the distance, Snellen, visual acuity, and guess what? Take a reciprocal. The resulting number is the required plus power to read. It's just a coincidence, a useful coincidence that can get you started. So a patient comes into your office, 2400 visual acuity, distance. What kind of a near ad do you estimate they're going to need to be able to read newsprint? Well, it's 400 divided by 20 is 40 over 2 is 20. So they're going to need like a plus 20 lens in order to be able to read newsprint. So you put the plus 20 lens up there, and you give the patient newspaper, and they hold the newspaper. They say, well, this doesn't help at all. I can't see. And that's because they're used to holding things at a normal reading distance. But take another reciprocal. It's a 20 diopter lens, so 1 over 20 is 0.05 meters or 5 centimeters away. So they're going to have to hold it up here to see, and now they'll be able to see it clearly. Now this coincidence is useful. It's a good starting point, but you do actually have to put the glasses on the patient and see if that's what's best for them before prescribing it. So plus lenses for near are one of the key things that are used, and we can give high adds in a bifocal of plus 4 to 20 diopters. You can see that there is a problem with that, which is the close working distance, but it does leave both hands free and gives a wide field of view. That close working distance can give extra problems if a patient has binocular vision, because they basically have to converge. If their working distance is 5 centimeters, they've got to converge 5 centimeters in order to see. Well, they're going to have a convergence insufficiency, so they're going to need, so they're exotropic basically at near, so they're going to need base-in prisms to help them be able to use the two eyes together. For patients who don't want that to be so limited to have to hold things 5 centimeters away, there's also handheld magnifiers. Handheld magnifiers allow for much greater variation in the eye to lens distance, so it's more comfortable for patients. However, it does require some degree of dexterity, and it's not as good for patients who have arthritis or tremor. Plus, there can be lighting issues. It's hard to get good light with the handheld magnifiers. There are lighted, so for the patients who have trouble with arthritis or are unsteady, then there are also stand magnifiers, which again allow for a variable distance from the eye to the lens. But again, there can be more trouble. They're less portable, and the lighting can still be an issue. So for that, there are lighted magnifiers, lighted hand magnifiers, which obviously give more vision. You can also, there's a little line in this one to help you find your place on the line, and you can get a decent amount of magnification. And there are whole varieties of these that are available for different patients. Everybody wants something a little bit different, and so it takes some time to work with patients to find these things. If we compare then plus lens near aids, the high plus add gives you both hands free and a wider field of view but a shorter working distance. The handheld magnifiers give a variable eye to lens distance, but it requires one hand and is more difficult for patients with tremor or arthritis. That's what I say here. The disadvantage is the smaller field of view. Handheld magnifiers are more portable. Stand magnifiers are more stable. For patients where that's not enough, there is also the option of loops. Loops, you can get even higher magnifications. They're basically telescopes with a near add on them. So they give a longer working distance, you see here, and they leave the hands free. But the depth of focus is limited, so it requires precise head position. You know this because you've used surgical loops. It's not necessarily that easy to get used to it. The field of view is smaller. They're going to be costly. And patients, even elderly patients with low vision, they don't necessarily want to be this conspicuous and have something that looks like that. So then there are electronic displays that can be used for reading. Closed circuit television, you can see this requires some manual dexterity to move it around on the page, but it allows for reversal of contrast. They can be expensive, although this particular model the patient got at a steep discount. And then there are computer scanners where it's a scanner and a computer display that turns the image on the page into something where you can get reverse contrast. You can even get it turned into speech if you have very low vision. Then there's also there are handheld cameras that are perhaps more intuitive than the closed circuit where you're, instead of bringing the material under a camera, these handheld cameras allow you to point the camera at the area of interest with a good depth of focus, so they're more intuitive. So to summarize the electronic displays, they have very high magnification, allow for contrast reversal, and can eliminate extraneous material, but they're expensive, they're generally not portable, and they require a degree of dexterity. So then there are non-optical aids that can be used, large numeral telephone dials, large print reading materials. There are black ink marking pens just so the patient can see what they're writing. There are masking devices that can be used for reading. And then there are signature guides, and these are especially popular with the younger relatives of older low vision patients. Just sign right here, Grandma. And then just in general, helping patients control their illumination to get the right amount of light on the page to be able to see. All of these non-optical aids, they're generally low tech, but they're things that can make a big difference to low vision patients. For distance, the choices are much more limited. There are telescopes that patients can use. For example, the need might be to see the blackboard or to see a bus sign. There can be monocular or binocular telescopes, handheld or spectacle mounted, and they can have adjustable focus or a fixed focus. These bioptic telescopes, they're built into glasses, but they allow for free navigation and hands to be held free. And the patient will just sort of tip their chin down when they need to see something in particular, and then otherwise the magnification is up there because you can't really walk looking through them or drive. But it is in some states it's legal to drive with this sort of a low vision aid because if this lets you get 20/40 vision, as long as your peripheral vision is intact. And then absorptive lenses can help control glare, can help patients with, for example, achromatopsia and dark adaptation, and help with mediopacities or albinism. Again, it's sort of a lower tech thing that makes a big difference to patients. The higher tech approaches, there are head-mounted video cameras out there, dual video monitors. You know, for some reason, this one just hasn't really caught on. And then there are implantable mini telescopes, which are in clinical trials now. You know, we'll see how they go. I mean, to me, it almost makes as much sense to just leave a patient aphakic and give them plus lenses, and then you get 25% magnification that way. But we'll see. So that's low vision, and now we'll move on to mirrors. And we'll talk about the laws of reflection. We'll talk about the different types of mirrors that are out there. Vergence calculations, the U plus D equals V for mirrors, basically. And then look at real and virtual images created using mirrors. So the laws of reflection are straightforward. The angle, when light is reflected off some surface, the angle of reflection is equal to the angle of incidence. So that the incident ray, the normal to the surface, and the reflected ray all lie in the same plane. All that says is light bouncing off a mirror isn't going to just change direction. Mirrors can be considered a lens that flips over the image space by reversing the direction of light. A plane mirror adds no vergence, it just reverses direction. A convex mirror adds minus vergence, a concave mirror adds plus vergence, like a plus lens. And we can apply that formula from this morning or yesterday or last week, U plus D equals V, to locate the images formed by mirrors. All you have to do is remember that the mirror is reversing the direction at the same time that the vergence changes. So a plane mirror forms an erect virtual image of a real object, and the image is as far behind the mirror as the object is in front. So that one outcome of this is that actually you only need a half-length mirror to see your entire self in, because if you start at the foot, the light comes halfway up the mirror and then comes towards your eye. It depends on what kind of shoe style you wear, though, because if you wear those really long, pointy shoes, then you know they're going to come closer. So then in order to see your shoes, you'd have a little more. But still, the basic idea is about a half of a mirror. The other thing that means is that as you move a mirror farther away, the image also moves further away, so the field of view stays the same no matter how far away a plane mirror is. It's the size of the mirror that gives your field of view and not the distance away from the mirror. Now, Connie West took some pictures of what it looks like in a mirror to demonstrate some of these principles. So here's a plane mirror, and you see that as the mirror is further, in both cases she still has an upright image, and that as we get further away, the image also moves further away, so the field of view doesn't actually change. Contrast this with what you see with a concave mirror here. In the concave mirror, the image is now inverted and minified somewhat when you're far away. But actually, when you're up close, the image is upright and magnified. And we'll do the calculations to show why that is. Then you can have an astigmatic, a convex mirror. And in a convex mirror, again, the image is upright, and it's going to be minified. And that's what this says. It says objects in mirror are closer than they appear. That means they're, what does that mean? No, it means that they're minified. And then you can have an astigmatic mirror, as you see from this oil tanker, where it has a flat horizontal meridian, but a steep vertical meridian, so you get different reflecting powers, and therefore different sizes in the two different dimensions. So let's do some Vergence calculations to show that we can do that with a mirror. And first, we just want to demonstrate that the image is as far behind as the object is in front. So we have an object that's 25 centimeters away from a mirror. Where's the image? Well, 25 centimeters away, we take a reciprocal, 1 over 0.25 meters. Don't forget to convert. 1 over 0.25 meters is 4 diopters, but it's -4 because it's diverging light. So then U plus D equals V. -4 plus 0 Vergence added by a plane mirror equals -4. But the light has reverse directions. So it's going this way with a Vergence of -4. So where's the image? Well, the rays of light are diverging on this side, so we have to create imaginary extensions of the rays of light back to a point of intersection on the other side of the lens. How far away is it? Take a reciprocal. 1 over 4 diopters is 0.25 meters, or 25 centimeters away from the mirror. So the image is as far behind as the object is in front, and it's an upright image. And it's a virtual image because it's imaginary extensions of the rays of light back to a point of intersection on the other side of the lens. So what about a concave mirror, and what is the reflecting power of a mirror? Remember the refracting power of a lens? Well, that D equals n prime minus n over r. Well, for a mirror, we have a very similar formula, actually. Well, first, before I say that, we'll say the reflecting power is actually just the reciprocal of the focal length of the lens. And the focal length is half the radius of curvature of the lens. So here's the radius of curvature of this particular mirror. That means the focal length is half that, and the power is 2 over r, 2 over the radius of curvature. Remember, D equals n prime minus n over r, but in a mirror, there's no difference in refractive index because it's just bouncing off the mirror. So n prime minus n becomes 1 minus -1, which ends up becoming 2 in a mirror. So 2 over r. Where do you draw a central ray when you have a curved mirror? Is it from the tip of the object through the center of the mirror? No, it's not. It is from the tip of the object through the center of curvature of the mirror. That's the central ray. So let's put all these things together then. Now we know the reflecting power as it relates to the center of curvature, the radius of curvature, and that the focal length is half that distance. So by the way, if that's the focal point of a mirror, that means if the focal point's half this distance, that means parallel rays of light coming in would be focused to this point. Or if you wanted to create a flashlight, you'd put the light right here at the focal point because then the rays of light would come straight out. All right, so let's look at Now, in a convex mirror, the central ray again passes through the tip of the center of curvature of the mirror. So in a convex mirror, you're always going to have an upright image because it's always in here somewhere. So let's put all these together then and do a calculation. So we have a 4 diopter shaving mirror, and we put an object 16.7 centimeters away. Where's the image? Well, it's a 4 diopter shaving mirror. That means the center of curvature of the mirror is going to be 0.5 meters away because the power is 2 over r. 2 over 0.5 meters is 4 diopters. Okay, and so now what's the vergence of light entering that strikes the mirror? Well, we take a reciprocal. 1 over 0.167 centimeters is negative 6 diopters. So we do u plus d equals v. Negative 6 diopters plus 4 diopters is negative 2. So the light leaving this mirror has a vergence of negative 2 diopters. But it's diverging light. So where's the image? We have to create imaginary extensions of the rays of light back to a point of intersection on the other side of the mirror. How far away is it? Take a reciprocal. 1 over 2 diopters is 0.5 meters or 50 centimeters away. Is it upright or is it inverted? Well, we draw a line from the tip of the object. Does it go through the center of the mirror? No. Tip of the object through the center of curvature of the mirror. There's our central ray. We know the image is here. We draw a line from the image location up to the central ray, and you see that the image is upright and magnified, and if it wasn't, it would be a lousy shaving mirror. Now with convex cave mirrors, they're interesting because depending on where you put the object, you can have, like I say, inverted and minified, upright and magnified. You can even end up with not just a virtual image, but a real image if you put it in just the right spot. So like so. So here's the object. It's just the right distance away. The rays of light here are converging, so you end up with a real image here. Or put the object here, you end up with a real image out there. And that's what's done here. You can astound your friends with optical magic. And I know that it's a real image because it says it right here. The real image Mirage projects is brilliant, full of color and details. So it's sort of projecting that image up on top of this disc, even though the marbles are down inside somewhere. Now, as an example of a convex mirror, let's consider the cornea. The cornea is a convex mirror with a radius of curvature of, remember this morning we said 7 millimeters, but just for this example we're going to say 8 millimeters, 7 to 8 millimeters. So the reflecting power of this convex mirror is 2 over r, 2 divided by the radius of curvature, or 0.008 meters, or 250 diopters. So the cornea is a convex mirror with a power of 250 diopters, actually minus 250 because it's a convex surface. Now wait a minute, some of you are saying in the audience, I could have sworn this morning you said the cornea has a power of 50 diopters or 45 or 48 or something like that, but certainly not 250 diopters. But this morning we were talking about the refracting power of the cornea. What happens to light when it passes through the cornea? Now we're talking about the reflecting power of the cornea. What happens to the light that bounces off of the cornea? The refracting power is 50 diopters, but the reflecting power is 250 diopters. And we'll see later today that you can use that reflecting power to determine the radius of curvature of the cornea, which in turn can then be used to calculate the refracting power of the cornea. So back to our question here. When we're looking at a person's corneal light reflex, where exactly is that in the eye? Is it in front of the eye? Is it on the cornea? Is it inside the eye? Well, the hand light is usually about 1/3 of a meter away. So then the light coming in is 1 over 0.33 diopters or minus centimeters or minus 3 diopters. U plus D equals V. Negative 350 plus negative 250 is negative 253. So, but it's diverging light, coming out. So where's the image? Create imaginary extension of the rays of light back to a point of intersection on the other side of the mirror. How far away is it? Take a reciprocal, 1 over 253 diopters is 0.004 meters or 4 millimeters away. So the cornea is the corneal light reflex is actually located, when we look at a patient's eye and we're looking at that corneal light reflex, it's actually behind the cornea. It's 4 millimeters behind the cornea. It's even behind the iris. Now, what if his eye was filled with blood? Would we then be able, would the corneal light reflex disappear? Well, no, it's a virtual image, so you can still, it'll still look like it's 4 millimeters behind the cornea, even if the eye is filled with blood. This is what makes Hirschberg testing so tricky, because you see as the eye rotates, the corneal light reflex is rotating on a 4 millimeter radius, whereas the eye itself is rotating on an 8 millimeter radius. So it's not an intuitive shift of the corneal light reflex as the eye crosses inward. And then the final part of this, or not the final part, but the next part of this section is prisms. And we'll talk about calibration of prisms, positioning, combining prisms, talk about Prentice's rule, which causes induced strabismus, image jump and image displacement, Fresnel prisms, oblique prisms, and chromatic aberrations. So a lot of different things to cover when we're talking about prisms. First rule or message or thing to think about in prisms is that it's a little funny because the prism power depends on the angle of incidence. This picture I took two prisms that had exactly the same power. They're both 25 prism diopter prisms. But you can see that they seem to have different powers because the image is shifted over different amounts. But that's because this prism is in the position of minimum deviation, whereas this prism, it's obliquely positioned. So prisms have different powers depending on the angle of incidence of light coming in. And the position of minimum deviation is when the angle in equals the angle out, like so. Anything that deviates from that, you end up getting more prismatic deviation. You see the way a prism works. Remember back this morning or yesterday or last week or whenever it was, we talked about how light is bent towards the normal to the interface when you go from low to high refractive index, and then away from the normal to the interface when you go from high to low refractive index. And with these angles configured as so, you end up with the rays of light sort of deflected towards the base, as if they were sort of draped over the top of the prism. So light is deflected towards the base of a prism. When you're using prisms in the clinic, you need to position them properly or you could end up with incorrect measurements. So in this case, this is called the Prentice position, where the back surface is perpendicular to the eye. This, by putting the back of the prism in the frontal plane, that simulates the position of minimum deviation, and that gives the least error when doing your measurements. So you see that if you hold, in this case, this was some numbers generated by David Guyton. If you hold this prism perpendicular to the visual axis, you get it measures 40 prism diopters, but if you hold it in the frontal plane, it measures 32. So let's say you grab a prism out of the prism box, and it's 32 prism diopter prism, and you measure, it says 32, and you do a cover test, but you actually hold it at an angle so that it's neutralizing 40, and you do your cover test, and now there's no shift. And you say, it must be, you look at the prism, you say, 32 prism diopters, it must be a 32 angle. But in fact, because you had the prism tilted, you were neutralizing 40, so the true measurement was 40. But it says 32, so you operate for 32, you end up with an undercorrection. You say, this strabismus surgery, it's a bunch of witchcraft. Which is true, but it doesn't help matters if you're not holding the prism in the right way. So we want the prisms, with plastic prisms, we hold them in the frontal plane. That's the position, if this eye is exotropic, that's the position of minimum deviation. Glass prisms you actually do hold that way, but nobody uses glass prisms these days. The glass prisms you hold with the Prentice position. Now, if you're trying to combine two prisms together, you end up with more surprises. In this case, you actually end up, you've combined these two prisms, and we can't see anything in there because we've ended up with total internal reflection of light. Now, what in the world is going on there? Well, what happens, and again, these are some Guyton numbers, but if you combine, say, just a 5 and a 40, if you stack two prisms, stack them so that they're touching each other, you end up neutralizing 58 of prism power. 40 and 10, you neutralize more than 100 prism diopters. Well, why would that be? It's just putting two prisms together. Why shouldn't 1 plus 1 make 2? Well, the problem is if you look at this interface and stack prisms between prism A and B, if we blow that up, the light, this first one, yes, it's position of minimum deviation, but then the second one, you see it's a weird angle that it's coming in that's nowhere near the position of minimum deviation. That's where the problem comes from. And so in order to combine prisms, you can't stack them like this. You can't put fluid between that either, because then you don't know what the power of the combination is. What you have to do is, you have to either, so you can't stack them like this, but if you position them like this, then you can do that. So here, both prisms are in the position of minimum deviation. It takes a little dexterity, but it can be done. I've done it. Put your thumb here, and one finger here, and one finger here. So that's one way to find the position of minimum deviation. The other way to do it is to just put one prism over each eye and put both of them in the position of minimum deviation like this. But this then introduces a new problem, which is that the way that prism diopters add up, which is that if you get into bigger prism powers, they don't necessarily add up. Now, if this patient has a big deviation like this, you see there's a 50 on this side, 25 on this side, you're going to be doing big surgery. So you would actually then, you could probably 3 muscle surgeries. So you'd like operate this side for 50 and this side for 25. You do 2 muscles on this side and 1 on this side. You should get them close. But how do those add up? Well, let's look at the definition of a prism diopter to explain why 1 plus 1, another reason why 1 plus 1 doesn't equal 2 when it comes to prisms. Prism diopters are a nonlinear measurement. It's a convenient way to measure prisms. You take like a laser pointer, aim it at a screen, put a little mark there. Now you put the prism in place, and you'll see the mark will go down, deflected towards the base by a certain number of centimeters. And if the prism is 100 centimeters from the screen and the light deflects down by 15, that's a 15 prism diopter prism. Now you may notice, I'd like to just point out here that we're talking about centimeters here, because all the day we've been talking about make sure everything's in meters before you do your calculations. But for some of the prism calculations I'm going to show you, you actually do them in centimeters. So that's 15 centimeters. What if the light was deflected down by 100 centimeters? Then that would be 100 prism diopter prism. But if it's 100 and 100, that's a 45-degree angle. So a 45-degree angle is the same as 100 prism diopters. Okay, so that's the definition of a prism diopter. So if you have a patient who has exotropia of 45 degrees of the left eye and 45 degrees of the right eye, we know that's 100 and 100. So is the combined deviation 200 prism diopters? We know it's 90 degrees, but is it 200 prism diopters? No, it's actually infinite prism diopters. 90 degrees translates to infinite prism diopters. And why would that be? Well, here I just showed you the 45-degree angle. The light's deflected down the screen by 100 centimeters, but if the light comes in and goes at a 90-degree angle, it's going to be deflected down. It never touches the screen. It goes all the way down, and it just never meets the screen. So a 90-degree angle is equal to an infinite number of prism diopters. And we can plot this like so, looking at prism diopters per degree, like this, and you see that it really is pretty much 2 prism diopters per degree up to about 100 or 150 prism diopters. But then it goes crazy, and it goes off to infinity once you get up to 90 degrees. So it's not that often that we're explaining to patients about their 173 prism diopter deviations. So for the most part, you can use this, and it's convenient because you can give the patient the numbers in degrees instead of prism diopters, something more relevant. Or I find it especially useful, being a strabismus surgeon. I'll say to the family, well, before the surgery, Johnny had an exotropia of of 30 prism diopters, but now after the surgery, it only drifts out by 15 degrees. So we've had some improvement, but we need to perform an enhancement. Actually, I liked that idea of enhancement, but it wasn't catching on, but I now call it an adjustment, suture adjustment. So we've already said how prisms displace light towards the base, and so if I was to take a prism, and I do this sometimes in a smaller group, if I was to walk up to this projector and take a prism and put it base down here in the pathway of light between the projector and the screen, everyone in the room would see the image would shift down on the screen. The whole image of the slide would shift down on the screen. But the funny thing is that instead of that, if I handed each one of you a prism and had you put it base down over your eyes, the image would actually appear to shift, the image of the screen would actually appear to shift up instead of down, like this. So why would that be? In each case, whether it's in the path of light to the projector or in the path of light from the screen to the eye, in each case the light is still deflected toward the base. But when you're viewing through a prism, you're seeing a virtual image. We have imaginary extensions of the rays of light here, and so the virtual image appears to shift towards the apex, while the real image is displaced towards the base. So this can become a clinical issue. Let's take a subject who has straight eyes. So this person has straight eyes, and we're going to introduce prism. So I'm going to come back over here again. We're going to introduce prism in front of his right eye. What kind of a strabismus does that induce in his case? Is it a right hypertropia or a right hypotropia? Well, when you look at this slide, your first instinct is to say, oh, well, the eye looks like it's lower, so it must be a hypotropia. But let's think about it a little bit more carefully than that. First of all, if we look at the corneal light reflex, you'll see that it's actually now displaced downward inside of the pupil, which suggests that the eye is looking upward. Okay, that's one way to look at it. So that's telling us maybe it's a right hypertropia. Another thing is, if we put base up prism in front of the right eye, how would you fix that? You'd fix it with base down prism over the right eye. But you know from your clinical experience, if you do this, that base down prism is going to correct a right hypertropia. Another way to think of it is, imagine that there's a little man standing inside of the eye pointing a laser pointer straight at you. So this left one's going to come straight at you. And now there's another little man inside this eye, and it was pointing a laser pointer straight at you, so it was coming towards you, but then this base up prism intervened, and so what happens? The light's deflected towards the base. So the light coming out towards you gets deflected up toward the base. So it's a right hypertropia. Now don't confuse yourself by thinking about what's the patient going to do to try to fuse. I'm just saying the patient, if you just do cover testing in this case, you're going to measure a right hypertropia because the light that's coming out of this eye would be deflected up towards the base. Now, and you'll see later why we're going through this exercise, not too much later. And so that's a right hypertropia. Now, lenses, while lenses can refract light, they also have prismatic power of their own. And that can lead to some trouble sometimes in patients. And the amount of prism that a lens induces is determined by Prentice's rule. Delta equals H times D. H is the displacement away from the optical center of the lens in centimeters. D is the power of the lens in diopters. I don't like it when people describe strabismic deviations in diopters because it confuses me. I like prism diopters for prismatic deviations and diopters for lens deviations to keep it completely clear. So delta equals H in centimeters times D in diopters. That's how much prism power you induce. And what kind of prism? Is it base up or base down? Well, it depends on where the optical center is. Now, what I'm showing here is the geometric center of the lens, which is just determined by drawing a box around the eye, and the center of the box is the geometric center. But that has nothing to do with the optical center of the lens. The optical center could be anywhere, and you find it by putting the lens in a lens without prism in the lens meter and moving it around until there's no deflection of light. The optical center in that previous picture would be right here where the dotted line is. That's the optical center, where there's no prismatic power. A plus lens, then, we can think of with this visual mnemonic. It's acting like two prisms that are base to base. A minus lens we can think of as acting like two prisms that are apex to apex. So if we're below the optical center of a plus lens, we end up with base up prism. Below the optical center of a minus lens, we end up with base down prism, and vice versa for above. So we can see that in this picture. This image is of a minus lens, and you see that the image is displaced. So a minus lens is like prisms apex to apex. So the image of the side of the head is displaced toward the apex, whereas this plus lens is like prisms base to base. So the image of the side of the head is displaced toward the apex, which is out here. Now vertical, you can also end up with vertical prisms like so. And Connie West was telling me about a patient who was referred to her to clear the eye after trauma, because he was seeing double after he had had some trauma to the eye, and there was a non-displaced orbital fracture, and the surgeon was taking the patient to surgery because of the double vision, because obviously he had an entrapped muscle even though ocular motility was full. And it turned out that the trauma had also bent his glasses like so and given him a vertical strabismus, and she just took the glasses and bent them back into place, put them back on, cured the double vision, and spared the patient from surgery. Now, plus lenses can exaggerate the strabismic deviation, but not in the way you might think. Here's some very strong plus lenses, and it's making the patient look esotropic, and because it magnifies the eye, and so it's going to make the cosmetic deviation, whatever it is, worse. But what does it do to the measured deviation? Opposite of what you would think. Here's big, strong plus lenses, plus 10, in front of a patient who's exotropic. We know we're given that he has a 40 prism diopter exotropia, but you see the eye now, the optical pathway is going away from the center of the lens, so he's experiencing some base-in prism, which reduces the amount of exotropia. And if you do the math, it turns out it reduces it to 30 prism diopters. Whereas a patient who has, and now if the patient has esotropia, he's going to get base-out prism, which again is going to actually, is going to reduce the amount of measured esotropia. And so with high plus lenses, you reduce, the measured deviation is less than what you might, than the true deviation. And in contrast, with minus lenses, you get an increase in the measured deviation instead of the true deviation. And the formula is 2.5% times D, where D is the spectacle power. So these are plus 10 lenses, so it's a 25% increase in the measured deviation for myopia, decrease in deviation for hyperopia. The mnemonic there is minus measures more. So do you use this? Do we use this clinically? Well, you at least consider it clinically. Yet another reason why I tend to use adjustable sutures in complicated patients, but it is at least something to consider when doing your strabismus surgery. I think that it may be negated in part because the minus lenses decrease the cosmetic deviation and make it harder to see your endpoint for cover testing. So here's a patient, he has these strong minus lenses, and that's really all you can see, but when he takes the glasses off, then you see that he actually has an esotropia. But it looks like less here, but it measures more with the glasses on. So the effective deviation is increased by the minus lenses, but the cosmetic deviation is decreased by minus lenses. So this brings us then to a favorite question, and that is that a patient comes into the office after cataract surgery, and, well, you know, your post-op result maybe wasn't quite what you wanted here, +1, +3 to 90, and in addition, he's seeing double when he tries to read. What's going on here? Well, let's think about the prismatic effect in reading position in this patient. We're going to then look at this in each of these lenses separately. 1 centimeter below the optical center. The right lens first. -3 sphere. We're below the optical center, so we're getting base down prism. How much? Delta equals h times d is 1 centimeter times 3 diopters is 3 prism diopters of base down prism on the right. Left eye. Well, left eye, we need to know just the power in the vertical meridian, so we need to do a power cross. We have our shortcut where we know the +1 is going to go on the 90-degree meridian. We know it's going to be +4 on the 180, but that doesn't matter. So all you care about is the +1 in the 90-degree meridian. So it's 1 centimeter times 1 diopter is 1 prism diopter, but this is a plus lens, so it's base up prism. So you've got 3 base down on the right, 1 base up on the left. Now, do those cancel each other out, or do they add up? Well, if he had 3 base down on both sides, he wouldn't have any strabismus. He'd just have some image dislocation. So these add up and cause more difference between the eyes. So it's a total of 4 prism diopters of prism power in the reading position that he experiences, and this is what's causing his double vision. So what can we do about that? Can we, oh, and what kind of, is it a hyper or a right hypo again? Well, it's 3 base down on the right. Let's think of it as 4 base down on the right. So if you got base down prism on the right, then the little man shining his laser pointer from the fovea out to the world, it's going to experience base down prism, so the light's going to be deflected downward. So it's going to be a right hypotropia or a left hypertropia. So this patient then, in the reading position, experiences a left hypertropia of 4 prism diopters. So what to do about it? Do you just prescribe 4 of prism? Just write 4 base, 4 base down on the left, say? Well, no, you can't do that because that works for reading position, but now he'll see double when he's looking straight ahead. So we have a problem because it's a difference in different positions of gaze. So you could say, oh, now we'll get fancy and we'll move the optical centers down to the reading position. But if you move them all the way down to the reading position, then again, you got the same problem straight ahead. You could move them maybe halfway down and hope you get lucky, that'll be tolerable prism in the 2 different positions. Or you could prescribe, you could give contact lenses, of course, or partially lower the optical centers, or you could give slab off prism. So slab off prism is a different kind of a grinding. This is an example of glasses that have had prism power just taken off the bottom part of the lens, slab off power. And the way that works is that it's just taken off the more minus lens. You can give the amount. It's a separate grinding center, and this can help the patients have no strabismus in reading position or in straight ahead gaze. And this may sound like a theoretical problem, but it's a real problem. Here's a live actual patient who had it. I've treated a few diagnoses in a few patients, including one who'd had, a CT and an MRI and an MRA and a CAT scan and a PET scan, and then his pet had a CAT scan. And but it turned out that he'd had double vision ever since his cataract surgery. He had strabismus in the reading position. So most patients will adapt or learn to fuse some amount of it, but you may have to give some slab off prism. So what a great question to ask, though, if you think about it, if you want an efficient question. Because here you've got to, what do you have to know to answer this question? First, you have to be able to know this, Prentice's rule, to calculate the prism power off center. Second is you have to be able to do the power cross thing to figure out just what's in the vertical lens power. What's in vertical versus horizontal meridian. Third is you have to be able to figure out what induced prism, what kind of strabismus is created when you introduce prism in front of the eye. Fourth is you have to know what to do about it and how to, how to actually treat with slab-off prism. So it's a very efficient question because it requires a lot of knowledge of different things in optics to be able to get to the end. So next I wanted to talk about image jump and image displacement. And it's always a little hard for me to talk about this because I think it's less clinically important than some of the other issues, but still worth at least addressing briefly because it can come up. So image jump is what happens when the visual axis crosses into the bifocal, and it depends on the style of the bifocal, whereas image displacement is what happens in the reading position once the eyes have settled into the reading position. And it's a combined effects of the lens and the segment. So what exactly do I mean by image jump? It's the sudden introduction of prismatic power at the top of the bifocal segment, right there. Just as you cross that line, the image will seem to jump. And it's worse the further you are from the optical center. So these round top bifocal segments are going to give you maximum image jump, whereas a flat top segment gives you minimal image jump, and an executive segment, the optical centers align, there's no image jump here. Progressive bifocals, too, would have no image jump. So it has nothing to do with whether it's a hyperope or myope. It's all to do with the design of the segment. On the other hand, for image displacement, we have to think about what happens in the reading position. And a flat top segment is going to act like a base up prism in reading position, whereas a round top is going to act like a base down in reading position. So that the net deviation, if you have a plus lens and a round top, you got base up on the plus lens, base down on the bifocal, those cancel each other out. So there's minimal image displacement. Oops. On the other hand, plus lens and a flat top, both of them are base up prisms, so you're going to get a lot of image displacement in reading position. In myopic patients, it's the opposite. Round top, you get a lot of image displacement because you got base down, but flat top, you got base down, base up. Those cancel each other out, so there's not much image displacement. So for the myope, the decision about round top versus flat top is easy because image jump is less through the flat top. Image displacement is left through the combination. So flat tops are always going to be better for a myopic patient. Hyperopic patients, you have to decide. Image displacement is better through the flat top, through the round top. Image jump is better through the flat top. So what matters more to a patient? Well, as far as I'm concerned, if somebody is bothered by, if they say, it bothers me when I do this, then I would say, don't do that. Right? I mean, image jump is just not going to be that much of a clinical issue for most patients. Whereas image displacement, if they're a nuclear power plant operator and they reach to push the shutdown button, they may end up hitting the meltdown button. So, all of humanity may be riding on your shoulders if you prescribe the wrong bifocals to a nuclear power plant operator, giving them too much image displacement in reading position. That said, the fact is that flat top segments are ubiquitous, they're cheaper, they're easier to give, and so most hyperopic patients still end up with flat top segments, and few, if any, will complain, but you do need to know just in case that that one patient comes across your office who's having trouble. Fresnel prisms can be are also known as press-on prisms. Fresnel figured out that instead of one big prism like this, if you have a whole bunch of prisms, one next to the other, you can still get that same prismatic power. You can get them up to 40 prism diopters. They're relatively convenient compared to ground-in prisms and certainly more lightweight, but they're not perfect. They're difficult to clean, and all this little diffraction and chromatic aberration gives you glare and reduced visual acuity. But in the office, something like this, patient comes in with a new onset small angle strabismus. You can slap the Fresnel prism on there and send them home with single vision, and it can be very satisfying as a short-term solution, at least for many patients. When you're prescribing Fresnel prisms, there may come a time when the patient has both vertical and horizontal deviations, and you have to note you'd have to know trigonometry to be able to calculate it. But one other way that Dave Guyton taught me is that you can measure if you have, say, 5 up and 8 out, you can take a ruler, measure 5 this way, 8 this way, then cut it out, and you can measure the angle in the trial frame and give your prism. You can stick on your oblique prism in that way. The power is this length, and the angle is what's shown there. When you are prescribing prisms, though, you do have to be, especially if you're prescribing a Fresnel prism, if you don't stick it on yourself, you see that if you say 7 prism diopters base 135, there's actually a 135 here and a 135 here. So you have to say 7 base down and out in the 135 degree meridian, or 7 base up and in the 135 meridian. If you're prescribing ground-in prisms, you don't have to do any of the trigonometry. You just say, 8 base up and 5 base out over the left eye, and okay to divide prism between eyes, and that will be enough. That's obviously a different prescription. And then finally, with regard to prisms, they induce chromatic effects as well. And I think, once we're done with this, we'll break for lunch. We'll probably break for lunch. So I could just go all day without even taking a single break, but it's okay. We'll stop. So prisms have chromatic effects. That is, remember, discussion of refractive index has to do with how much the light slows, but different wavelengths will slow the light different amounts. And so white light is dispersed for this reason, where blue is bent most and red. The red rays, they're sort of more, they're the longer wavelength, and they just sort of cruise through and don't get deflected as much, whereas the high intensity blue short wavelength gets deflected more. So blue is bent the most. Thus, you get all the colors of the rainbow when you pass white light through a prism. And that's all very pretty, but it can cause problems in the eye, because not only do prisms have chromatic aberration, but lenses do as well, such that blue rays of light are focused closer to the lens than red rays of light. Blue rays of light come to focus sooner than red rays, and that means that you can get chromatic aberration in the eye. And it actually is, if you model it, it's pretty significant. It's a 3 diopter difference between the ends of the spectrum from blue to red. Although it's fairly significant, it's not really, we're sort of adjusted to it, and so it doesn't disturb our lives for the most part. And we can actually use it in the red-green test, which doesn't use a 3 diopter difference. You take filters and create a chromatic spherical difference of 0.5 diopters. So the duochrome or red-green test looks something like this. You have black letters on red and green backgrounds, and you adjust the sphere until the letters are equally clear on both sides. And what that means is that the red rays are as far behind the retina as the green rays are as in front, and that puts yellow light in perfect focus on the eye, which is optimal for viewing in white light. We generally start from the fog direction. That is, you give too much plus at first, you make the red clearer, and then when they say the red's clear, that means they want more red, so you give them more minus. So the advantage of this is, I don't personally use this because I'm just very stingy about giving minus power. I'll start with too much plus, and then I won't give the next minus unless they can actually read more letters. However, if you're doing multi-center studies of, say, refractive surgery, where refractive refraction is the outcome, this is one way to control it from many sites, and many clinicians do swear by this test as a great way to control for accommodation. So to review then what we've covered in other optics of note, we've covered magnification and low vision, how they work together, mirrors, and quite an extensive part of prisms. And what we'll be talking about next will be the most practical aspects of optics, including instruments and how we use them, prescribing tricks, and then optics in the office, that is what patients will present with and how you would approach and manage those patients. Now that we've had lunch, let's begin with part 4. And this is the final part where we're trying to put everything in increasingly more clinical relevance. And so I simply call it practical matters, where we'll review our formulas. We'll talk about prescribing glasses and some tricks related to that. Then we'll review instruments and how they work. And finally, a section I call Optics in the Office, where patients present with certain complaints, and you have to translate that into what does that mean about their glasses, or what do you look into their refraction that's a problem. So we officially have 1 hour to cover these topics. I may run over a little bit, but should be able to come close to that. So here are those formulas again. Remember, the most basic formulas of Prentice's rule, the Vergence formula, U plus D equals V, you kind of know that. Focal length is the reciprocal of the power. You see, by using them and applying them, they become more useful to you. Spherical equivalent is sort of trivial. And then the power calculations, yeah, that's a little bit more complicated. Definitely something you'd want to look at, say, the day before you were being tested, just to make sure you remember them. But I think I've repeated them enough that they at least make sense to you, including the SRK formula. It's a good idea to know that, just to, mainly because of the changes that you would make with changes in axial length or Ks. And then the magnification formulas, and we're going to revisit these as we look at some of the instruments that we work with. One I just said, image distance over object distance, but then the transverse is the square of the axial, and then a simple magnifier versus a telescope and spectacle magnification. So that's it. That whole wall of formulas breaks down into these concepts that we've covered to some extent over the course of this day. So let's then talk first about, in this section, about prescribing glasses, retinoscopy tips, high index lenses, how to improve myopic lenses, dealing with night myopia and aphakic spectacles, what to do when a child won't wear glasses, prescribing astigmatic lenses, and working with a high-powered Jackson cross cylinder. So during retinoscopy, how do you modify the value obtained at neutralization to obtain the final refraction? And I've mentioned this earlier, but think about what we're doing when we're doing retinoscopy. We're taking the far point of the eye and we're putting it at the peephole of the retinoscope. And so, but if we gave that as the glasses prescription, then the patient would be in focus on the peephole of the retinoscope, and we don't want that. We want them in focus at infinity. And so we need to move the far point to infinity, and we do that by subtracting the reciprocal of the distance to the patient from the number that we get. For most patients, it's 2/3 of a meter. Reciprocal of that is 3/2, or 1.5 diopters. What if a patient has a difficult to interpret retinoscopic reflex? Here's a LASIK flap gone bad, and that's going to be a very irregular retinoscopic reflex. How do you work with that? Well, one is, don't forget, you can move closer. So sometimes, even in a child, I'll move till I'm just 10 centimeters away, and at least that gives me the cylinder and one compared to the other. And it's a little tricky because it's 1 centimeter one way or another is a whole diopter at that distance. But it's basically you would subtract 10 from that number. So move closer. Concentrate on the center of the reflex, as I mentioned with spherical aberration. You get better and better as you do more retinoscopy on just looking at the central part of the retinoscopic reflex. If the astigmatism is irregular, then consider a contact lens over refraction, because that'll take away a lot of that irregularity and give you the best visual acuity you can get. You can always try the autorefractor. It might not work if it's not possible to retinoscope. You could get up with a bad number. You could just go ahead and throw up random numbers and do a subjective refinement of the refraction. Or another option is to use the stenopeic slit. And we don't really have time to go into how to do a stenopeic slit refraction, but it involves finding the major axis of astigmatism, using sphere to neutralize, and then going 90 degrees away and using sphere to neutralize that, ending up with a power cross that you then convert to glasses prescription. Or you could just prescribe the patient pinhole glasses, which will neutralize any refractive error, and it's a form of natural vision therapy. Now, what are high index lenses? Well, high index lenses are generally plastic lenses with a refractive index of 1.66 and up. They're thinner lenses and lighter weight. And why is that? Well, remember the equation, D equals n prime minus n over r. Well, r is the curvature, but if n prime minus n is a bigger number, then you don't need as much curvature to get the same diopters of power. So if you need less curvature, then the lenses are going to be less thick at their edges. So generally, high-index lenses are helped. They are going to be more expensive than ordinary plastic. Some have less light transmission. Some have more chromatic aberrations. So they're not perfect, but they are definitely have advantages. There are even glass lenses that you can get in Europe that have a 1.8, and patients swear by them. You can't get them in the US because they don't meet safety standards here. So if your patients always go to Germany to get their glasses made, then that's probably why. Patient comes into your office, says, gee, doc, can't you do something about these thick glasses? They look terrible. And you say, yeah, they do look terrible. So what can you offer to this patient? Well, how do you improve the appearance of high minus lenses? Well, again, we just mentioned one method. Well, before we get to that, make sure the patient's not over minus. Now, it's not like he's wearing minus 20 glasses. You're not going to get him to minus 2, but if you can knock another diopter or so off, that wouldn't hurt. So cycloplegic refraction. Next would be to use smaller frames, because the curvature, the more curved they are, the thicker they get as you get out to the periphery. So if you could have very small frames, they're just not going to look as thick at their edges. So that's a simple way. And the lenses can be beveled and polished at their edges in certain ways. And then the key, the money answer is, use that high refractive index material, because then you use less, you need less curvature to get the same refractive power. And then plastic versus glass, well, that depends, because as I just mentioned, some kinds of glass are actually less heavy, but at least in the US, you do better with plastic. A flatter base curve for the front of the lens, that is, I mentioned earlier that lenses have this sort of meniscus shape, so that the front tends to have plus power on it, even for myopic patients. But if you flatten that out, then you have to scoop less out of the back to get the same myopic correction. And then frames that hide the thick edges can help as well. And in real life, you would also offer the patient contact lenses or possibly refractive surgery, depending on their situation. So that's the different ways to improve the appearance of high minus lenses. 27-year-old patient returns to you after careful refraction. He's complaining of continued trouble with distance vision, especially at night. I seem to be night blind, he says. What are some causes? Well, after you've ruled out retinitis pigmentosa and patient unable to find their way to the seat in a dark theater, but just having trouble seeing road signs at night, then you want to look for the causes of night myopia. And that would include pupil dilation. So in the dark, the pupils get bigger, so there's more spherical aberration, which increases the myopia because of the positive spherical aberration. Plus, just a bigger pupil is going to reveal irregular astigmatism as well, which further degrades the image. Second is the length of the refraction lane. When we refract a patient, it's in a 20-foot long lane indoors, but when they're in a car, they're looking at signs that are 100 feet away or more. And so we want to, so the patient's not truly corrected for infinity if you refine the refraction in the office. To correct for infinity, you subtract that distance from the end of the exam lane, which is 1/6 of a meter, from the final prescription to put it truly off at infinity. Well, you're not going to subtract 1/6 of a diopter, but you could put an additional minus 0.25 into their glasses. Then this is a little fancier answer. Lower light levels cause a Purkinje shift. That is, photoreceptors are more sensitive to blue in low light. You can tell that from watching television, because they always show that it's nighttime because everything is blue, has this sort of bluish hue when they, but photoreceptors are more sensitive to blue in low light. And remember, from chromatic aberration, that's going to move the focal point anteriorly and make the patient more myopic. And then finally, in the dark, there's not as many accommodative targets. Patients may focus on a headlight and over-accommodate and fog himself to further cause night myopia. So all of these things can be mediated by giving a little bit more minus in the glasses. He's 27, so he can take being over minus probably, but as patients get closer to being presbyopic, they may have to have separate driving glass, sort of night driving glasses that over minus them slightly if they really are complaining bitterly about this condition. Problems with aphakic spectacles. Well, we don't deal with aphakic spectacles much, but we do have a lot of little high hyperopes running around in pediatric ophthalmology. There's a ring scotoma secondary to the prismatic effects of the edge of the lens. There's pincushion distortion, sort of the opposite of what I showed you when I turned the indirect lens upside down. The magnification that we discussed earlier, and the weight and cost of these spectacles. Sort of intuitive stuff, but worth at least mentioning explicitly while you're thinking about it. What if a child won't wear his glasses? What can you suggest? Well, a lot of times it's more to do with the frames than anything, because some opticians just don't have the selection or don't know how to fit kids. I mean, gee, I wonder why he doesn't like wearing these glasses. Perhaps because they cover one eye and they're made for a 32-year-old. They're actually the same glasses that that other guy was wearing. So the frame needs to fit properly. Opticians may not want to deal with kids and not take the time, and they have to be adjusted frequently because they get bent all the time, and a kid whose glasses don't fit, he's not going to say it's bothering me right here. He's going to put the glasses in the toilet. Consider a short course of cycloplegia to remind the patients why that the glasses actually do help, hyperopic patients, the glasses do help them see better. Who would have more trouble adjusting to contact lenses, a presbyopic, pre-presbyopic myope or hyperope? This sounds like almost a trick question, because you would think that as long as the refraction is corrected, it should be the same at near. But remember, at near, it's diverging light coming into the eye, not parallel rays of light. And so glasses, spectacle lenses, are going to see a different vergence than contact lenses. Furthermore, the power of the spectacle lens is going to be different than the power of the contact lens because of vertex difference changes. And so we could work through the math, but I'm just going to tell you to remember that it's the myope. Myopic patients will have more trouble adjusting to new contact lenses because there is a greater accommodative demand accommodating through contact lenses than through glasses in the case of myopia. The opposite is true as in hyperopia. So the vergence from the near target is greater after entering the eye through a contact lens. There's also a prismatic effect that can help you remember if you can't completely memorize it, want to figure it out. Minus lenses, remember, act like base in prism when the eye converges. Well, that's going to help the myopic patient converge when reading through minus lenses. You take those away, now they're going to have to converge all the way on their own. What are the disadvantages of progressive addition lenses? Why don't all patients wear them? Well, to get this channel of variable magnification through the no-line bifocals, you end up with this peripheral irregular astigmatism. These channels, the designs can vary. They can make them wider or narrower, speedier, increase in power, or less speedy, but the end result is this kind of distortion. So an architect, a draftsman, an art historian, these are the kinds of patients of mine who've had trouble with these progressive lenses and have had to switch to a segmented bifocal. The segment height is also difficult to adjust, and so if it's off by a little bit, either they got to go too far down to get the power, or they're getting some of their near power when they're looking straight ahead. How do you deal with a patient who's not accepting spectacle correction of astigmatism? Well, why would a patient have trouble with astigmatic correction in glasses? Well, this is what happens, is you get this kind of distortion of the image from the astigmatic correction, and the greater the vertex distance, the more. So, and not only is it the distortion, but there's another more subtle problem that develops, and it has to do with your binocular visual system. That is, here's what a door might look like to a patient who has astigmatic correction in both eyes that they're not used to. So each door looks a little distorted, it's true. But what you also get is you get this little bit of disparity, retinal disparity between the two eyes. Well, what's your binocular vision system primed to do? It takes retinal disparities and it builds them up into a three-dimensional perception of the world. And you can try to kind of cross your eyes and look at this image and get the two doors to sort of fuse into one. And if you do that, then you'll see, I can sometimes do it, it's pretty exaggerated, but what you'll see is the door isn't just distorted, but it looks like it's coming towards you. And that's just what the patients, they say. They say, oh my God, I put these glasses on and the floor's coming up at me and the walls are caving in. And it's not just because squares are oblique, it's because they have binocular distortion that's very disturbing to them. So how do you fix it? Well, you want to get away from oblique astigmatism if you can, or to reduce the astigmatic correction. You can actually try to fix it by reassuring the patient and just asking them to stick with it, and it'll get better. And even in older patients, I've found that that's possible to do depending on the patient. The longer it takes for the patient's older. If you can reduce the vertex distance, ultimately that would mean contact lenses. They're not going to cause much distortion. But if they happen to have some odd frames that kind of stick out, more than usual or something, then that would be one thing. It's more of just an answer to give you, but than anything I've actually prescribed. Cylinder lenses are ground both on the inside as minus cylinder or on the front as plus cylinder. They almost never ground on the front as plus cylinder anymore, but every now and then that's done, and that can exaggerate the astigmatic distortion. So minus cylinder lenses have less distortion. If those things don't work, then you do have to compromise visual acuity either by rotating the cylinder to 90 or 180 so you don't have that oblique distortion, or simply reducing the power of the cylinder, eventually trying to work the patient up to their full correction. There's always contact lenses or even refractive surgery to consider as well, of course. And my brother's friend Jack was noticing the body piercing trends and gave me this suggestion of a way to reduce the vertex distance by biocular piercing. Just take the little pierce here and then hang it. Then you can reduce the distance from the eye to the lens in this method. I haven't seen this catch on just yet. Why are there different Jackson cross cylinders? That is, you may not have, there's only one on the phoropter, but if you look around in the drawers of the office, you'll see something that looks like this. It's not a spoon. It's a Jackson cross cylinder, and there are different powers up to plus and minus 1. And the reason is that the poorer the visual acuity, the more difficult it would be for the patient to say which is better, 1 or 2. And of course, and the end point of Jackson cross cylinder is when they say they're the same. And so if the patient has 2200 vision and you're flipping a plus and minus a quarter, they're not going to see a difference. So you'll say, which is better, 1 or 2? They're going to say, it's the same. You'll say, good, we're done. But you actually haven't helped their refraction. So lower visual acuity, if you really want to refine the cylinder, you need the higher power Jackson cross cylinder so that they can see that difference. I just used that the other day with a 8-year-old child, and it actually worked. The fellow was stunned. So those are just some practical, aspects of prescribing glasses in patients, adults and children. And what I want to go to next is to look at the optical principles of some of the ophthalmic instruments that we use on a daily basis, and to try to better understand exactly how it is that they work. So we're going to talk about everything from the lowly trial lenses and lens clock to lens meters, retinoscope, how keratometry and slit lamps work, applanation tonometry, then fundus lenses and lasers. Trial lenses. So we use trial lenses in the office, and you would think, again, 1 + 1 should always equal 2, but if you don't actually separate the spacing just right, it doesn't add up. But the trial lenses are designed to have that kind of additivity, and the trial frames, are actually designed to take advantage of that, to put the lenses in the proper position. Those trial frames, they're awfully expensive for something that breaks all the time, but I guess that's why. So when you're using the trial frames, you want the numbers to face forward, and you want the high power sphere to go in the rear cell, because that's where the vertex distance matters most. And then any cylinder is going to go in the middle cell, and if you need another quarter low power lens, that would go in the very front cell, or prism, or whatever. So you would think that you're being a good industrious and studious, and you have this kind of new prescription for a patient, so you're afraid they might not accept it. Maybe it's got some cylinder in there that might be too much. So you go and you put it in the trial lens frames, and you have the patient walk around the office, and they say it's okay. They still might come back and say that the glasses are no good. And the reason is that they don't fully simulate dispensed spectacles because of differences in the aperture, in the base curve, And so just be prepared for that eventuality. A lens clock is something that you use in the office to determine the curvature of a lens. The dial here reads in diopters of surface power, assuming a certain refractive index of the lens behind it. So the conversion to surface power uses that refractive index of crown glass for this style. So there's a little pin here that moves back and forth, and depending on the position, the dial moves to a different place, and then you can judge the power of the lens on the back and on the front. There's a different kind that's made for plastic lenses, so you would want to be careful because usually the situation is the patient likes their old glasses, they don't like the new glasses, and you're trying to see a difference, and you can use the lens clock to tell. And if you use the wrong lens clock, you'll end up scratching their only glasses they ever liked in the world. So you want to be careful about that. So the way you use it is you can measure, you can see if there's a difference in base curve between eyes, and you can also see is there cylinder on the front surface or on the back surface of the lens. Probably the most typical scenario would be a patient comes into your office and they're on their way out the door after you've already finished the examination, and they say, "Oh, by the way, doc, can I have a new glasses prescription?" Now, of course, you didn't even do the refraction. You've already dilated the pupils, and you just want to go home. And so you just write out, you copy the exact prescription that they were already wearing. You say, here's your new prescription. So they go back, they get the new prescription made, and they come back 2 weeks later and they say, "Doc, these new glasses you prescribed, they're terrible. They're nothing like my old glasses. Those were great." So what are you going to do? You measure them in the lens meter. They're exactly the same power. And so perhaps there's a difference in base curve, the curvature, overall curvature of the lens. So you get out the lens clock and you compare the two, and you see if the base curve is different. And if so, then you have your diagnosis. Now, meanwhile, of course, your partner's examined 3 patients and signed 2 of them up for surgery. So if you're smart, you never touch one of these things. But that is probably the most typical application. Lens clock. Next is lens meter. So the lens meter is used to measure the power of a spectacle lens, and when I say lens meter, I want you to think optometer principle. So what is the optometer principle? Well, think about trying to build a lens meter when how do you figure out the power of an unknown lens? Well, you might take a target and you might position the unknown lens next to your own eye. This is you, the examiner. And if you move that target to and fro, when you get it to just the right spot, you'll have parallel rays of light coming out. So you'll know that's then you take the reciprocal of the distance, and that's the power of the lens. The problem with that is that as you get closer to higher powers, tiny movements give big shifts in the dioptric power. Plus, how do you measure a minus lens that way? Then you have to slip some other lens in place or something. So it just doesn't work well. So the optometer principle says if you, there we go, so that's the power of that lens, but it doesn't work well. So the optometer principle says you add a second lens called a standard lens. You put the unknown lens at one focal point of that lens, and the target goes at another. When there's no lens in there and the target's at the focal point of the lens, then you, the examiner, are going to see parallel rays of light. However, if we now slip an unknown lens into the other focal point of the lens, of the standard lens, that's going to cause the rays of light to be unparalleled and out of focus. So now we've got to turn a knob, move the target, say closer in this case. So now parallel rays of light are coming out. So the advantage of the optometer principle with this standard lens is you get a linear scale and you can go from plus to minus power in measuring an unknown lens. So that's basically what a lens meter is with a little bit added on. So here's the lens meter, here's the target, it's illuminated. You turn a knob, it moves it back and forth. There's the standard lens inside of the lens meter, and here's where the unknown lens goes. Then you throw an astronomical telescope on there just to eliminate the examiner's refractive error and to further enhance the detection of parallel rays of light coming out. So that's all there is to it. So when you're using a lens meter, the way that I do it is at the beginning of the day, I'll actually have nothing in the lens meter, set the knob at 0, and then adjust the eyepiece starting start by fog myself by turning the eyepiece out, then just dial it just in until the reticles and the target come into perfect focus. Then you know it's zeroed for your eye and should be accurate for the rest of the day. This is what you see when you look in a lens meter. The cross target with a sphere line and the three lines for the cylinder for the two meridians of astigmatism and power. When you're measuring the lenses, you want to measure the back vertex power. That is, the temples should be away from the examiner, except for the bifocal power add, which you measure when you're measuring the front vertex power, which is with the temple toward the examiner. That's especially important with high plus lenses. You can otherwise get fairly big differences if you try to just measure back vertex power for both. Now, normally, when you put a lens in and you look inside, you'll see this target exactly centered in these rings, and that's fine. But when you have prism in there, then you'll see a displacement like so. So you hear this crossbar is displaced upward, and up here, right there, is a number 2. So that's 2 prism diopters, that's 1. So this is 1.5 prism diopters, and what you see is what it is. So it's 1.5 prism diopters of base up prism in that lens. Now, when you move the lens, if the lenses are, say, high plus or high minus, when you move them around, then that's going to change. But if it's a lower power, then it's more clear that that's the answer. I'll show you in a second what to do when they're higher power lenses to control for that problem. But if you forget this rule and you just want to use a neutralizing prism, you could put prism in the path of light to recenter that cross in the middle. So that's what's being done here. In this case, it must have been horizontal prism because there's base out prism that's neutralizing. And so that means the glasses must have base in prism. There's also, in some lens meters, this little area to put in a tri-lens prism, or the ones that they sell now have a knob that you can dial in more or less prism. So this is what you do, this high-tech method to see where the line of sight passes through the spectacle lens. You just put a dot right in the center of each pupil, and that's where you measure the prism power. So then you don't have to worry about where the optical center is. In fact, sometimes the optical center can become displaced either by accident or on purpose and generate prism power. I even had a patient who had glasses not unlike these, who came back to the office, and she used to have an esotropia of 10 or something, and she came back, and now the esotropia was gone. But when I forget, I had to measure the glasses for something, and I discovered that the optical centers were like here, temporally, and here. And I got more history, and it turned out the glasses had fallen, had broken, or she dropped the glasses, both lenses had popped out, so they just popped the lenses back in. But they switched them, because they're symmetric lenses, and so they ended up decentering the optical centers. So then I needed to write a new prescription anyway, because the glasses were broken, and I put on there, I put on the prescription, decenter optical centers, 1.5 centimeters temporally each eye. Got a call back from the optician, well, we can't do that. And I said, well, what do you mean? You just did it on these glasses when you fixed them last week. So it's sort of like that guy who goes to the airport and he says, I want this bag to go to Albuquerque and this bag to go to Chicago and this one to Denver. And they say, we can't do that. And they said, well, you did it last week. Decentering optical lenses. Again, if nobody laughs, I still get paid. You can also measure lens prism power with lens meters. They'll just spit it out for you using various approaches. The retinoscope, what I want to mention about that is that it has a linear filament that produces, for the most part, divergent light. Now, the sleeve position can create convergent light, but it's only in special circumstances that you want convergent light going into the eye for retinoscopy. It should be divergent light most of the time. So you can, if it's a new retinoscope that you're not familiar with, you can do what I call the sleeve test, which is aim it at your sleeve, and then push the sleeve all the way up, see if you can focus the light, push the sleeve all the way down, see if you can focus the light, and if you can focus the light, then that's not what you want. You want it to where you can't get it into focus, and that's where you position the sleeve for retinoscopy. How do we get these with and against movements when we do retinoscopy? Again, let's go back to the definition of what happens at neutralization of retinoscopy. At neutralization, as soon as the light goes into the eye, all the light coming back from the eye is focused at the peephole of the retinoscope, so it all fits through the peephole, so the pupil appears to fill with light the moment any light comes in. Neutralization. If, however, the eye is not in perfect focus, say the far point is back here, well, now when the light enters the eye, some of it coming back fits through the peephole, but the rest doesn't. It hits the edge of the peephole, so only part of the pupil appears to have light coming back, and the top stays on the top and the bottom stays on the bottom. That's with movement. However, if the far point is in front of the examiner, then what happens is the same problem. Not all the light gets through, but now the top has crossed over at the far point, the bottom's crossed over, and so because of that crossover, you get what appears to be against movement. Next comes the concept of optical doubling, and this is going to tie back into the Vernier acuity discussion that we had some months ago. So remember the definition of a prism diopter is that 100 centimeters, a 10 prism diopter prism will displace an image will displace the light by 10 centimeters. So in this case, we have a pair of sunglasses. And we have a 10 prism diopter prism. And if we can work it to where we can see both the object and the image at the same time, then we'll see that they're separated by 10 centimeters. What if we want to measure how high these sunglasses are? Well, let's turn back the prism, say it's variable. We'll dial it down to, say, 5. So now the separation is 5 centimeters, so that means that we can measure the height of these glasses must be 5 centimeters when the bottom of the image tops the touch of the object. Well, you say that's kind of a cumbersome way to measure something, but the beauty of this is that if those glasses, that the image and the object, if there's any movement or high magnification, they're going to move at the same time. So say those sunglasses are on a child, and say the child's jumping up and down on a trampoline, it's okay because the image and the object are moving at the same time, and so you can still make that adjustment to where they touch each other. Well, we don't go measuring necessarily glasses on children who are jumping on trampolines, but we do have to measure things on the surface of the eye under high magnification. And so this ability to use optical doubling or image doubling is invaluable. And it also takes advantage, you'll see later, of your Vernier acuity because you're trying to make a line join to a line. So let's talk about that a little bit more, and in particular with regard to corneal curvature assessment. When we want to know how curved the cornea is, we generally do keratometry, optical or automated. Today we'll focus on just optical keratometry. There are other ways to do it too, we'll briefly mention. But for optical keratometry, you want to know how curved is the cornea. Well, how curved is the cornea means how strong. One way to determine that is to ask how strong a mirror is the cornea. And one way to determine that is to say how big is the image created by the cornea. So to determine that image, we project a mire onto the cornea and measure its size. An optical keratometer then looks at the average curvature over the central 3 millimeters of the cornea, measuring the size of a reflected mire. The size tells you the reflecting power. The reflecting power then allows you to determine the radius of curvature. The radius of curvature then allows you to infer the refracting power. And it uses optical doubling to do that. Let me show you an example. This is the Javel-Schiatz type of ophthalmometer, keratometer. It projects these two mires, the box thing and the Space Invaders thing, onto the surface of the cornea. So then you end up with an image that looks like this. Now, first of all, if you're not in line with a principal meridian of astigmatism, these are going to be just skewed like this. So you rotate, so you can rotate this thing to get them in line with the principal meridian. So we do that, rotate the Myers. Now we're in line with the principal meridian. Now in this case, they're at the correct separation. But what if you have a very curved cornea? If the cornea is very steep, it's going to be a stronger minus power, so the image is going to be smaller. So now we're going to turn another knob, and it's going to change the separation of those Myers to bring the images closer together. What if you have a weak or flat cornea? Then the images are going to be big, so you turn the knob, change the separation, increase it this time, and get your exact result. So that's basically what you're doing when you're doing keratometry. And you do a vertical meridian measurement, and you do a horizontal meridian measurement. So with this style, you have to do 2 measurements, but you get your 2 powers, and then you read it off here. You get the radius of curvature from the size of the Meyer, and then that corresponds with a certain power in diopters, assuming that the refractive index of the cornea is 1.3375, which it generally is. So that's that question about, someone asked me at the break about converting from radius of curvature to power, diopters of power. So now if the person was an alien from outer space and you did keratometry, then the radius would still be correct, but you might not know if the refracting power is truly this because you don't know what their cornea is made of. It might have a different refractive index. So you see, not only are you saving people's lives by diagnosing a ciliary body tumor through a refractive index change, or saving the world by keeping nuclear power plant operators in the proper bifocals, but you're also even learning how to do intergalactic keratometry. The Bausch and Lomb keratometer is similar in its concept, but this projects the Myers and allows simultaneous measurement of vertical and horizontal. And it uses image doubling to help you find your endpoint. That is, here if the keratometer is out of focus, you adjust it, you get a doubled image and adjust it to and fro until you have a single image. So it's using your Vernier acuity to help determine that point of focus. And then if you're off axis, again, you turn it until you're on the axis of the principal meridians. Now you adjust the horizontal till it just lines up like so, and then you adjust the vertical till it just lines up, again using Vernier acuity to make that precise measurement of the endpoint. A powerful cornea is going to have smaller Myers, so you have to move them closer together. A weaker cornea, bigger Myers. Here's an example of a flat vertical meridian, so you're going to have to increase the separation more vertically than horizontally. Then you look at the number on the keratometer to get your answer. Again, there are automated keratometers that automatically measure the size and position of these reflected Myers. There is also, of course, corneal topography that looks, one form that looks at these projected Myers and then uses a computer to determine the separation and to convert that into a map of the corneal curvature over the whole surface of the cornea, rather than just an average keratometry that optical keratometers will calculate. So that's keratometers. Next is a slit lamp. And the key, there's Goldstrand again. When he wasn't busy winning a Nobel Prize, he was off inventing the slit lamp. And that is the key advance. When I say slit lamp, I want you to think common pivot point. So there's an illuminated slit that's projected into the eye, and a viewing system of a binocular stereo microscope with individually focused eyepieces. But the key is that they're imaged over a common pivot point, so that as you move the slit lamp to and fro, the slit stays in focus, and the place where you're looking at the slit also stays in focus. This gives you an optical cross-section of the eye focused, but no matter what kind you look at, there's the common pivot point of this one. There's the common pivot point of this one, and there's the common pivot point of this one. They're all on that pivot point. And there's even, to really adjust the focus, you can actually drop a little focusing stick into the common pivot point, which I'll show you in a second. You can adjust the magnification by either changing the eyepieces. These happen to be 10x, but there's usually somewhere you'll find in a drawer in the office somewhere some other magnification eyepieces, or by changing the objectives on this stereo microscope. See, it's 1x here and 1.6. When you flip this little lever to the other side, then the objective lens, you see, flips in and out of position like so. The other style of slit lamp has a kind of an odd looking magnification change, because you see it goes 5, 12, 20, 30, then 12 and 8. It seems a little like, why would they do that? It just doesn't make sense, and it's kind of annoying when you're flipping through. Well, the reason is it's actually an elegant solution to the problem, because in that circle, if you look at the diagram here, there are little Galilean telescopes. And so a forward Galilean telescope would give you a 30 of magnification, but the reverse Galilean telescope gives you 5. Same with 8 versus 20, but here it's 12 and 12 either way, and that's because, see the little dotted line in there? There's no telescope in that one. So it is very elegant, but it's still kind of annoying. Here's the focusing stick I mentioned, and so you can use that to make sure that the slit and the eyepieces are all focused in the same place at the same time by adjusting accordingly. If you find yourself getting headaches when using the slit lamp, it could be that the eyepieces are way out of alignment. So just with any other instrument, if you have a focusing stick, great. If not, you can use the edge of conjunctiva or something in sort of where you can really tell that the slit's in focus the way it's supposed to be, and then you adjust one eye at a time. Pachymetry is next. We use that to measure corneal thickness and anterior chamber depth. And we'll just mention it briefly because it's kind of not really used anymore, but there is an optical pachymeter that used to be used attached to the slit lamp, where you get, again, a simultaneous image of the object and the image through a doubling prism. Adjust the doubling prism, use your Vernier acuity to find an endpoint, and that gives you the anterior chamber depth when the front of the lens touches the back of the cornea in the image. Now this is generally done with either ultrasound biomicroscopy or even anterior segment OCT. You get a much better measurement of corneal thickness, endothelial thickness, etc. The applanation tonometer. The applanation tonometer is a split field plastic prism, we'll explain why in a second, where increasing the force against the eye expands the diameter of a fluorescein enhanced tear meniscus. And what you want is, once you have expanded that tear meniscus to exactly 3.06 millimeters, then the pressure against the eye in dynes is equal to 1/10 of the intraocular pressure in millimeters of mercury. Now, so what you have to do, imagine trying to do applanation without this split field prism. What you'd have to have in the slit lamp is a little ruler attachment or a reticle, and you'd have to flatten the cornea till you had it just exactly that diameter. Now that one, it looks like it's probably a little too much force, so then you'd sort of back off, and that's not really quite enough. But there, that looks about right, or maybe not. Is it right or isn't it? Hard to say exactly. So it would be an imprecise measurement. So what we have in the applanation tip is a split field prism that separates the images by, guess how much? 3.06 millimeters. This way, when you have too much force, it's obvious because these overlap. So now you back off a little bit. Whoops, that's too far, too little force. Now the circle's small, too small, so they're separated by too much. So then we increase it again, and that's just right, where exactly 3.06 millimeters of separation. Notice that you're using your Vernier acuity to find that break in the line and make that precise adjustment. Now, why do we have there's this little red line on the tip, thing that holds the applanation tip. What's that doing there? Well, that has to do with when an eye has astigmatism. Because if astigmatism is present, then the applanated area will be elliptical, so then it's hard to tell when you have the right diameter. So how do you compensate, and what kind of a problem does that lead to? Well, here's an eye with a high astigmatism, flat horizontal meridian. So in fact, mathematically, this is the proper reading, because you want to be at basically 58 degrees, I believe, to the major axis of the ellipse, to get the exact measurement. So this is actually right, but it looks like it's wrong. So you back off on the knob, and then you end up with an artificially low reading. If you measure, so say you rotate the appling tip now 90 degrees and measure this way. It's like, oh, now that looks like it's not enough separation, so you're going to incorrectly dial up on the knob and get an artificially high reading in this meridian. Ah, there we go. Now we're oblique, and so this is the correct one. So if you can be oblique, then you get it just right. So the red line, if you put the red line in the axis of minus cylinder, that places the split field prism at the proper oblique orientation for measuring astigmatism. Now, in my practice, I usually don't bother to do that. I just measure this way, and I remeasure this way, and I take the average of the two. And that is just as close an estimate as measuring obliquely. And I actually managed to cure a child of his glaucoma post-trauma when he had a large astigmatism from the corneal trauma and also had glaucoma. I cured his glaucoma by measuring the pressure in the correct way. And again, why 3.06 millimeters? I mentioned this, they didn't forget to put a 0 on there. This is the force against the eye in dynes. And so it's 1.4 dynes when it's 3.06 millimeters applanated corresponds to 14 millimeters of mercury pressure against the eye. As we say there. Next comes fundus lenses. And have you ever wondered why, like if you can see the cornea so great and the lens so great, why can't you just push the thing that much closer to get a nice view of the retina without having to deal with putting an extra lens in place? Trying to do that here, and it's just not working. The problem is, don't forget about this front of the eye has that 60 diopters of power. And so as you move the slit lamp closer, the light coming in gets converged, and you can never get more than about a third of the way back from the lens to the retina. So fundus lenses have to undo that in one of a couple of ways. One would be to essentially flatten the cornea, and the other is to use indirect ophthalmoscopy. So here we have a minus lens, and another is a minus lens. So the minus lens diverges the light on the way in, so now it can make it all the way back to the retina so you can see it, and that's the ruby lens. So the ruby lens is a minus 55 diopter lens. It gives you an upright image of the fundus with minimal magnification distortion. It's actually a very quality image, but it's kind of cumbersome to use, so we tend not to see it used very much anymore thanks to the indirect methods. The Goldmann contact lens, you can think of it as a minus lens. You can also think of it as just replacing the front of the eye with a flat surface and neutralizing all the corneal power, again, to get you all the way back to the fundus, has the advantage of the mirrors that let you look into the periphery. The 90 diopter lens, completely different optically. This is a plus lens, not a minus lens, and it gives an aerial inverted image, just like with indirect ophthalmoscopy. That's why when you put up that 90 diopter lens, say you're focused on the cornea, and then you put up your 90 diopter lens, you have to pull the slit lamp way back because you're pulling it back to look at this aerial image of the retina. The 4-mirror gonioscopic lens also has a central flat area. Don't forget to look at the fundus, so that's one more way to get in. The operating microscope, just very briefly, it has a binoculars, a magnification changer, and an objective lens. You can, when you change your zoom, you'd like it to stay in focus, and ideally you do that before you do your surgery, setting the eyepieces to 0 and the zoom to max. Then you focus the microscope, moving it up and down on like a 4x4. Then you change all the way back out to 0, and now you focus the eyepieces again. With those steps, you can make the microscope parfocal so that it won't go out of focus as you zoom in and out during the procedure. The direct ophthalmoscope, we mentioned earlier, uses the optics of the patient's eye as a simple magnifier. But notice that if the patient is myopic, then that means there's a plus error lens in there, so it's like a Galilean telescope. So you get extra magnification looking in a myopic eye, whereas the patient's hyperopic, it's like a minus error lens inside the eye. So that's a reverse Galilean telescope, minified. So that's why you may have noticed with the direct ophthalmoscope, it's a little easier to look into the eye of a hyperopic patient than a myopic patient because it's also less magnified. And then one thing is when you're doing direct ophthalmoscopy, only some of the light is making it all the way to the examiner. The indirect ophthalmoscope has this condensing lens that captures the peripheral rays and brings them into the observer's eye. It used to be done with this monocular indirect ophthalmoscope, but then Scapins invented the binocular indirect ophthalmoscope. Oh, this is just the field of view again. So 7 degrees with direct ophthalmoscopy, 25 degrees with the indirect because of the condensing lens capturing those peripheral images. When you're doing binocular indirect ophthalmoscopy, the challenge there is to image both pupils and a light source in through the patient's pupil without getting a lot of glare to occur. But that's basically what's accomplished with this. If you've ever, so you're forming basically an image of the examiner's pupils in the patient's pupil, like so the light in the examiner. If you've ever looked at the small pupil type of indirect ophthalmoscope and turned the knob and wondered what happens, what you need to do is you need to move the pupils even closer together now. That's like a 15 millimeter separation. And the light source is up there. If you've got to image those into a smaller pupil, you pull the trigger and voila. Now they see everything's even closer together. So you can get in through the smaller pupil with that setting, but you're going to get less depth perception and more glare. So when possible, you can use it in the large pupil setting, but if you have to, at least you get an image in the small pupil setting. And so because of this, having to do this, it does reduce your pupillary distance from 60 millimeters down to about 15. This, by the way, is a prism that has total internal reflection right there. So that's 60 down to 15 millimeters, which would reduce your perception of stereo by about 4-fold. I learned that the hard way when I was a medical student, all gung-ho, wanted to, wanted to do everything I could, and there was a grand rounds with a live patient there and a line of people examining with the indirect scope. So I borrowed the lens from the resident and put on the indirect hat and took the lens and wham, hit the patient right in the side of the head with my lens. Oh, sorry about that. My depth perception was reduced. I didn't know that at the time. I only learned that a couple of years ago. So what kind of magnification do we see when we're looking at when we're looking into an eye? The magnification is the power. It turns out, if we do the math, it's the power of the eye divided by the power of the indirect lens that we use. It's transverse magnification. So we know the power of the eye is roughly 60 diopters. And so for a 20 diopter lens, the magnification is going to be power of the eye is 60 over 20 is 3x, power of the eye over the power of the lens. Now remember though, transverse magnification squared gives you the axial magnification. So that means if it looks 3 times bigger across, and it's say a nevus, then it's going to look 9 times deeper. So you're going to get some distortion of depth when looking at the indirect ophthalmoscope. But then, remember what I just said, is the eyepieces reduce your appearance of that depth by 4-fold, so that the axial elevation actually appears to be 9 divided by 4, or 2.25x. So this nevus that you're looking at in the eye is 3 times across, but 2.25 times bigger. So there's a little bit of flattening or depth distortion that occurs. Different lenses, though, give different powers. If you look at the 30 lens, it's a 1-to-2 flattening. If you look at a 15 diopter lens, it's a 1-to-1, no flattening. So you say, does that mean we should actually be using 15 diopter lenses when looking at tumors in the eye? And the answer is no, but you need to be aware that if you switch from one lens to another, you're going to get a different perception, and you shouldn't interpret that as a change in the tumor. Retinal angiography, we already discussed briefly. Fluorescein absorbs in one wavelength, emits in a different wavelength, and you use filters to get the two, to get only the wavelength of interest back out. Lasers. How do we make, what is laser light? Laser light is monochromatic, that is, all photons have the same wavelength. It is coherent, remember that? All the peaks are in sequence. That means you can produce an interference pattern. It is polarized, remember that? Orientation of the electrical field of every wave is in the same orientation. It is directional, that is, it doesn't spread. You can bounce a laser off the moon and get the light back. In total, you can deliver a large amount of energy to a small area with laser light. There are different kinds of lasers. There's continuous wave and pulsed. Continuous wave, the energy per application is varied just by changing a shutter setting. The longer the exposure, the more the energy you deliver. But a pulsed laser, the power comes out as a burst, and so the watts vary over time. And so you keep the time of delivery constant, but measure it in joules, which is a watt delivered for 1 second. So if you see a laser has a power setting in joules, it means it's a pulsed laser, not a continuous wave laser. The three basic ingredients to a laser. We need a pulsed power sort to make energy. We need an active medium to emit photons, and we need a chamber with mirrors at opposite sides. So let's look at that, and I'm going to walk over here because it's easier to stand next to the laser while we build one, just to help understand how it works. So here's our chamber, and we're going to put a mirror inside of it, 100% reflecting this side, 98% reflecting on this side, 2% transmitting. Now we're going to fill it up with some source, with a photon emitter, whatever we choose. That's usually what the laser's named after, whatever this substance is. And now we got to get it to release photons, so we pump it with an electromagnetic pump. So this pump, every time the pump hits the emitting substance, more photons are released. So you pump, 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 and each time the pump comes out, more photons are released in an exact sequence, so that's what gives you coherent light, is that steady pumping in the right sequence. Then the light bounces back and forth, on average, because that one's 98% reflecting, 2% transmitting, on average 50 times, and on the 50th time it's gone back and forth so many times you have directional light, so that on the 50th time it bounces out, and out comes coherent, directional, monochromatic light. And that's your laser. Monochromatic because those photon-emitting substance only emits one kind of photon. So what do you do with that kind of power? Well, you can burn things, you can blow them up, and you can sublimate or dissolve them, basically, separate them by sublimation. You burn things with photocoagulation. Energy is absorbed by the tissue, and you get a rise in temperature. You can blow them up with lots of energy, plasma formation and shock wave, or you sublimate by disrupting covalent bonds. Let's look at some examples. Burning things, photocoagulation. We use different colors of light from blue-green to infrared. The blue-green's absorbed by most everything it passes through, RPE, xanthophyll, iris hemoglobin. But then as you go closer and closer to red, red is really absorbed mainly by melanin, and diode is absorbed solely by pigment epithelial melanin, nothing else. So with a diode laser, doesn't matter, you can treat from the outside through sclera or from the inside through pupil. It all goes into the melanin and creates an intense heat in the pigment epithelium only, and that's how you burn the retina. The YAG laser is infrared light, where you have these high power pulses that are focused into a very small area, causing plasma formation, optical breakdown, basically a little explosion. And so absorption is not necessary, and that's why we can use the YAG laser to cut semi-transparent membranes like the posterior capsule of the lens. And then we have the excimer laser, which is at the other end of the spectrum in ultraviolet, high power ultraviolet radiation. That's absorbed by all eye layers, even by the water, even by tears. So the cornea gets most of the energy. You actually want to remove the tears to treat with the excimer laser. And the damage, it's not burned, it's not blown up, it's more like an insurgency. It goes in and it disrupts the covalent bonds that hold the tissue together, that hold the molecules together. There's no heat, there's no fuss, things just sublimate. And so this was one of the early excimer lasers when they were thinking of using it more like a knife, and you get this nice, beautiful mushroom cloud of sublimated material disappearing off into space. It looks beautiful, but of course if you're trying to treat a big patch with the excimer laser, that's going to cause an irregular ablation and diffraction and distortion and glare and all those things. So you need a fan to blow all that stuff out of the way before the next pulse comes in. Otherwise you'll get bad pulses. So that's ophthalmic instruments. And as the final step, I just want to talk about some key symptoms. And we'll run over by a little bit. I don't think by too much. I want to talk about some key symptoms that will bring patients to you that may have something to do with the optics of what they're looking at. And just, I mean, if you think about it, if you were, say, an oral examiner or something, you've got to have clinical scenarios that are relevant that still allow the candidate to show their understanding of optics in a clinically relevant way. So we're going to talk about double vision, bad glasses, poor vision, and headaches and asthenopia. It's not a super long section. So patient comes into your office with double vision. Well, the very first thing is to find out if it's monocular diplopia or binocular diplopia. And the diagnosis is simple, but not as simple as you think. Have the patient cover one eye, and if the double vision is still there, then it must be monocular diplopia. But you have to have them cover the right eye, because what if the left eye has monocular diplopia, the right eye doesn't? If they cover their left eye, their monocular diplopia will go away. That just happened to me just like Saturday. I saw a patient post-op because I'd done her adjustable suture strabismus surgery, and she said, "Oh, the double's worse than ever. It's everywhere I look. It's horrible." And so I brought her in. I thought I'd have to readjust. But it turns out she had a little epithelial defect that crossed right across her pupil, and she had monocular diplopia. And when she covered her left eye that had surgery, yeah, everything was single. When you covered the right eye, though, she had clear double vision, went away with a pinhole. So the causes are then surface problem. Just refractive error alone can cause monocular diplopia. Don't know if you've ever experienced that. I've certainly seen it. Midpoint in a refraction, sometimes the patient will tell you that. Irregular astigmatism. A lenticular irregularity, such as cataract. Only rarely can a retinal problem cause this. That's the only one that wouldn't go away with a pinhole. The most common scenario, I would say, is a patient comes into your office, monocular double vision. You sort of narrow it down either to dry eye or to an early incipient cataract that's just enough to cause this double vision. And once you explain it to the patient that they don't have a brain tumor, show them that it goes away with the pinhole, they're usually satisfied and then you can address it as best you can. Okay, patient comes into your office. It's definitely this time, it's binocular diplopia. You cover one eye, it gets better. You cover the other eye, it gets better. With both eyes open, they see double. So what do? Well, you do cover testing, prism and cover testing to look for strabismus, of course. But sometimes the strabismus can be subtle and not that visible. You want to look for prism in the glasses. Now, sometimes the prism can be there by accident. Just as I said, a patient drops their glasses and the lenses go in upside down or they get reversed or something like that. Even more subtle is, and again I've seen this, a patient might have had a superior oblique palsy and an optometrist 10 years ago gave him prism glasses, and each refraction after that someone's kept the prism glasses going, but now finally someone gives them a prescription and doesn't realize that there's prism in there. Now all of a sudden with the new glasses they have double vision. I guess I'm jumping ahead of myself, but you can do a red glass or other sensory test, and really if it's true binocular diplopia, for the most part, except for what we'll just talk about, it's more of a strabismus issue that you kind of go into that mode. New glasses are no good. I described the scenario, give the patient their new glasses. It's especially challenging if the new glasses were the exact same prescription, but you do want to compare, if possible, get the old glasses. Compare the axis and the power. Compare the base curves. Look for prism, unintentionally ground in, intentional prism that's been ground in, or unintentional because the optical centers are off axis. Consider trauma to the glasses, as I've also mentioned. Look for the astigmatic grinding, the front and the back surface. It gives you a chance to sort of show off your knowledge of lens clocks. Look for different coatings or tints. All of these things can potentially have something to do with the patient who's unhappy with glasses. We were just discussing at the break a patient who might have had a reduced distance, plus they had a myopic shift at distance, and so the bifocals used to be good, but now because you've taken away plus from the glasses, that means their effective bifocal power is also reduced. That could be another cause of new glasses no good. Yeah, and here we are, check bifocals. So the power might be off for the reason that I just said, or for other reasons. The segment height could be off, especially in the progressive ads. The design may have changed from progressive to flat top or vice versa. A patient just recently, again, bitterly complaining about her new glasses, and it was because if she moved her head side to side, professor type, right, engineer type, if she moved her head side to side, then she'd see this wavering in the image. So that's why her new glasses were no good, and she went to a segmented bifocal. Check the refraction. Look for cycloplegic refraction because maybe they've been over-minused. Look for a big change in the cylinder, and look for a rapid change such as cataract, and then that throws us into that whole differential diagnosis. All these things are sort of things that you kind of know. You would know when you're sitting in front of a patient and have them in front of you, but you might not know when you're sitting in a hotel room across the table from someone who has a book that has the answers in it. Poor vision after refraction. Remember I said a long time ago when I started, it was a month ago or so, that you do your best refraction and the vision's still bad. Well, why would that be? Well, maybe your refraction wasn't that good after all, so put the pinhole occluder up now after you're done with the refraction. See if it gets better. Say it does get better. Well, maybe your axis is off, or they still have poor vision, so get out the high power Jackson cross cylinder so you can really truly refine the astigmatic axis in a way that the patient can make their choices. Look for dumb stuff. Maybe the eye chart contrast is off, the bad lighting on the eye chart. Consider subtle disease. You're still allowed to have disease, even in the optics section and in real life. Latent nystagmus would be one notable and notorious thing that can cause reduced vision with one eye covered. Recheck vision with both eyes open to see if it gets better. And dry eye as well. Often patients, even in the course of a refraction, I'll have to tell them to just stop and blink a few times and the vision will magically improve. A lot of magic in this. Headache and asthenopia, another big topic. Patient comes into your office complaining of headache, tired eyes when the glasses. So they're not saying they're no good, but they're specifically complaining of headaches. Cover testing, look for those phorias and tropias. Again, maybe induced by glasses that had optical centers that were off. Look for prism in the glasses. Again, either new prism that shouldn't be in there or prism that used to be in there that you didn't notice and forgot to check. Check the refraction, of course. Latent hyperopia would be a primary cause of asthenopia and headache. Not enough plus power, causing the patient to have to work hard to accommodate, or overcorrected, over-minused, again causing the patient to over-accommodate. Or a patient may just have early presbyopia and be having to accommodate in that way. So in the last couple of minutes, just this what we covered in this part 4 was a review of the formulas, prescribing glasses, instruments, and a quick rundown of optics in the office and how that works. And I just want to say that I know that a lot of you are studying for an exam right now, and you're mostly worried about that. But I'd like you to think of it as an opportunity, if you can sort of get to that level, that some of this stuff actually makes a difference. Some of this stuff really does help you, make you a better doctor. Furthermore, it can make things more interesting when you're taking care of patients. It can help you take care of that, anyone can get the 90% of patients, but it can help you take care of that last 10% of patients who have tricky problems, who need a little more thought, thinking outside of the box, and working on it a little bit more. And as a result, it makes your life and your practice, enhances it in a different way than it would otherwise. So that's really my job today. And optics, I know for all you say about it, just last Sunday in the New York Times Magazine, we'll take this out of context. This is taken out of context, but the quote was appropriate. The beauty of optics is in the eye of the beholder. So thank you all for your attention today, and I hope this does help make you better and more satisfied doctors. Thank you.